Hello, check. Those online, can you hear me?
Yes, sir.
Okay, cool. See. और आने वाला है क्या आपको कुछ आइडिया नंबर में? All right. Good evening, everyone. I think since there's just a few of us, I think I'll just get to know you guys. So you can just introduce yourself.
I'm Yash.
Yash.
I'm from Rajans, and this is my first offline class.
Okay. Okay.
I'm Jabran. I'm also from Rajans, and this is also my first offline class.
Okay.
I'm Vikram from Startical.
Okay.
And
Vishal. Umkar. Okay.
I'm Arya Datta.
Okay. So you guys have not you've not attended the previous lectures.
No.
Oh, okay. So what is Rajans actually?
Rajans is a junior college in the opposite to Andheri Sports Complex.
Okay. So record ho raha hai na? हाँ. So okay. So you have not done anything in rotational.
Actually, there were a few lectures before this. This
Huh.
should be the 9th lecture that we
हाँ
I haven't been making notes because we have a school going on. I mean, the exams are
हाँ
starting,
हाँ हाँ.
so I wasn't really attending classes.
We had online lectures
Yeah.
before that.
By
Okay.
the
Till-
week, so.
Yeah. All right. So what I think we can do is, I mean, so I'll teach today, okay? And you guys let me know, let's see how we can do it. So I'll teach as in when you find something new on the board, okay? Okay, you see me writing, talking about this concept or talking about this term, and you don't know what it is about. Let me try and then, just help you, explain that and just in a way catch up. But the idea will be we'll get through today's lecture and we'll see what can be done to cover up what you missed, right? Because I think it's 9 lectures, maybe 2-3 hours, so some 20 hours of stuff that we need to cover up. So we'll try to do that, but let's also try to make sense. So if you feel that you're not understanding parts of what is going on, just allow me to explain. Okay. Cool. So all right, so we are learning rotational mechanics. Let me just try. Works. Okay, rotational mechanics, and I heard that basically what Sir has covered so far is he's covered moment of inertia, right? And you guys don't know about that yet, right? Okay, fine. Just soldier through this class and try to pick up what you can. So moment of inertia हुआ है, and फिर torque equal to I alpha वो equation के साथ काम करना हुआ है ना? Work energy theorem, kinetic energy of a rolling body, ठीक है? Okay, cool. All right, so let's continue, ठीक है? And as in even for the other guys who already attended the previous 9 lectures, if while I'm teaching, if there's something you feel ki, sir, can you explain this again? Sir, I forgot this formula. Yeah, I forgot this concept. You want me to explain it again? Please don't hesitate, even those online. Please don't hesitate to, okay? Just maybe raise your voice and ask me to do that. Cool. So heading लिख लो, okay? Let's take out your notes and लिख लो instantaneous axis of rotation.
So you're gonna start rolling motion today.
So I've talked to sir based on what all is left. Yes, rolling is left. I think उन्होंने बोला था कि rotation plus translation, conservation of angular momentum in that context होना बाकी है. And instantaneous axis of rotation, ये पढ़ाया है क्या तुमने? नहीं रहे, not yet.
Well, we have only thought about the axis of rotation,
Okay.
like not the instantaneous.
Okay, so we'll get to rolling. Okay, I would say we'll get to rolling in another maybe in the next lecture or something like that. Okay, so today we'll start with this instantaneous axis of rotation, and you will see why, because learning about this is a little crucial to understand certain things we're going to do even in pure rolling. Okay, so let's go instantaneous axis. Just excuse me for my handwriting because I'm still getting used to this. See, that's quite blinding. Axis of rotation. Instantaneous axis of rotation. And I'm going to use this term so often. Okay. Now let's give it an abbreviation. So the IAOR stands for the instantaneous axis of rotation. Thoda dictate karunga. I think just me writing on this is going to take some time. I hope those who are online can hear me clearly, right? To write alongside. So iska definition likh lo. Okay. So it is the axis about which a body rotates. It is the axis about which a body rotates. Which is at rest at any given instant. It is the axis about which the body rotates, comma. The axis ke baad bhi comma. So it is the axis, comma, about which the body rotates, comma, which is at rest at any given instant. Okay. So for instance, let's just take some simple examples. So for instance, imagine you have a rod which is rotating about a hinge. Here's a very simple one. A rod rotating about a hinge. So what is going to be the instantaneous axis of rotation for this system, for this rod? The hinge. Yeah, very simple. Why? Because the hinge is at rest, right? So this, because this has zero velocity,
You're supposed to do this thing.
okay. Whatever, because it has, okay, that's zero, okay, because it has zero velocity. Because it has zero velocity, this is going to behave as the instantaneous axis of rotation. Another example, I'm sure sir has mentioned this word called as pure rolling, right? And we'll come to rolling again. We'll understand this again in more detail, but pure rolling, it seemed like he had mentioned it. Can someone just, those who know about this, can you take a guess where will be the instantaneous axis of rotation for any pure rolling body?
It would be the center. The center.
Okay, so let's check whether this lines up with our definition. Yes, the body is rotating about the center, okay? But
it's not at rest.
It's not at rest. Very nice. So center खुद आगे जा रहा है ना? Center खुद आगे जा रहा है. So it doesn't seem to fit our definition.
So no point will be the instantaneous axis of rotation.
Okay. So interestingly, there is a point. And what is that point? Oh.
Outside the body.
It could be outside the body. Instantaneous axis of rotation could very well be outside the body. But in this case, as we will revisit, pure rolling का definition होता है. Just imagine a wheel. Pure rolling का definition होता है कि a kind of rolling motion जिसमें this lowest point does not slide on the road, right? Whenever you've driven a car or driven a bike or driven a cycle, you must have noticed कि the rubber of that tire is not really sliding on the road. वो जब extreme case में तुम brake दबाते हो और वो skid होता है तब actually slide हो रहा है. That's when you can sense your tires are wearing out. Normally क्या होता है? There's no slipping on that surface, right? तो क्या होता है? Basically ये point, the lowest point प्योर रोलिंग का डेफिनेशन ये है, वापस आगे भी देखेंगे, but lowest point is always at rest, and the lowest point over there becomes the instantaneous axis of rotation. At this instant, the wheel seems to be rotating about this point.
So it changes constantly.
And it changes constantly. मतलब ये अगर आगे जाएगा कुछ देर बाद वो वाला पॉइंट नीचे आएगा, ठीक है, वो पॉइंट नीचे आएगा तो वो नया एक्सिस ऑफ रोटेशन होगा. Hence the name instantaneous. हर इंस्टेंट पे there may be a different axis of rotation. तो in simple words, these are two very simple examples. Rod about a hinge के लिए hinge is the IOR, and pure rolling में the lowest point over there is going to be the IOR. ठीक है. Okay. Cool. All right. Up, let's see steps to. So these are simple examples. Sometimes the examples may not be that straightforward. Sometimes they may just give you a random body, or random body के 2 point के velocity देंगे, and they'll ask you to locate the IAOR. So these are some steps you can apply to locate the IOR. So heading लिख लो, steps to locate the IAOR. Steps to locate the IAOR. Okay. First step, draw lines from each point. Draw lines from each point whose velocity is given. Draw lines from each point whose velocity is given. Okay. Perpendicular to the given velocities. Perpendicular to the given velocities. Okay. These lines, same point, these lines will contain the radii. Okay, RADII. These lines will contain the radii. I'll explain what this means. We'll just write the steps down first. Step 2. If the lines intersect at a point, that point is the IAOR. The lines intersect at a point, that point is the IAOR. Step 3. If the lines overlap, the IAOR is the point on the line, whose velocity is 0. Is the point on the line whose velocity is 0. Okay? So let's understand this.
In example 2, we say the velocity at that point is 0 because there's a forward velocity of the whole body which is due to translation. And there would be an equal velocity at the opposite direction as well, right? That due to rotation.
Okay.
So which is why velocity is
0. So you guys have learned circular motion in school. So what he's basically saying is, so just we don't want to get into pure rolling right now again. Sorry. Yeah, we don't want to get into pure rolling again, but just a quick explanation of what he just said. So he said कि ये जो तुम्हारा center का velocity है, ठीक है, center का velocity, center of mass का velocity in pure rolling R omega होगा. एक तरीके से ऐसा देख लो, IOR is the center of the circle about which these guys are actually rotating. ठीक है, तो इस बॉडी का हर पार्टिकल सर्कुलर मोशन कर रहा है ग्राउंड के फ्रेम में इस पॉइंट के बाद, इस एक्सिस के बाद. तो ये सेंटर ऑफ मास यहां से r डिस्टेंस दूर है, राइट? तो सेंटर ऑफ मास का रेडियस फिर r हो गया, अगर एंगुलर वेलोसिटी ओमेगा है तो उसका वेलोसिटी आर ओमेगा हो जाएगा. नाउ व्हाट ही इज सेइंग इज, ही इज सेइंग कि तो ये पॉइंट का अगर कहानी देखोगे, जस्ट अनदर वे ऑफ सेइंग द सेम थिंग, ये पॉइंट का कहानी देखोगे तो ये पॉइंट पहले तो सेंटर ऑफ मास के साथ साथ आगे जा रहा है. कितने वेलोसिटी से आगे जा रहा है? VCM. तो ट्रांसलेशन के कारण यू कैन इमेजिन द लोएस्ट पॉइंट VCM से आगे जा रहा है. ठीक है, सेंटर ऑफ मास के हिसाब से. बट सेंटर ऑफ मास के अबाउट बॉडी खुद घूम रहा है विथ एन एंगुलर वेलोसिटी ओमेगा, राइट. तो सेंटर ऑफ मास के रिस्पेक्ट में ये बॉडी घूम रहा है, जिसके कारण ये लोवेस्ट पॉइंट आर ओमेगा से पीछे आ रहा है. राइट, दैट्स द फॉर्मूला. इफ अ बॉडी इज रोटेटिंग अबाउट अ पॉइंट विद रिस्पेक्ट टू दैट पॉइंट, ठीक है, इफ दैट पॉइंट इज लाइक द सेंटर, तो आर डिस्टेंस अवे that guy will see this guy move with a velocity of r omega, right? So that's what basically he was just trying to say. We'll unpack this again when we revisit pure rolling, but this is what he was saying. Center के साथ साथ आगे जा रहा है VCM से, center के respect में घूमने के कारण पीछे आ रहा है r omega से, and in pure rolling these two are equal, so that cancels out. That's okay, that has to cancel out for this to be 0. Okay, so either way you can say VCM is r omega is the condition for pure rolling. Okay, don't get scared, we'll revisit that again. Let's try to understand the steps we had written. So what I'm trying to say is, if we have a random body, okay, let's just say this is some random body जिसके 2 points का velocity हमें दिया है, ठीक है, let's say V1 and V2. It's a random rigid body जिनके 2 points का velocity ऐसा दिया है. What we are trying to do is, the first step says draw lines perpendicular. So draw lines from each point जिसका velocity दिया है, 2 दे देंगे, and draw lines perpendicular to those velocities. तो देखो ये एक line हो गया, ठीक है, and वो एक और line हो गया, ठीक है, ठीक है. So I'm drawing lines perpendicular to the velocities. And what am I trying to do? I'm saying कि यार ये particle ऐसा move कर रहा है, but ground के frame में कोई तो एक point होगा जिसके about ये circular motion कर रहा है. We're trying to locate that point. So how are we? So we're trying to locate the center of इसका circular path. Center कैसे locate करेंगे? तो मैं radius draw कर रहा हूँ. Circular motion में velocity tangent के along होता है, and radius is perpendicular to the velocity. तो यहाँ पे radius draw कर रहे हैं. तो ये हो गया इसका radius. We don't know where it ends, but ये line के along इसका radius lie करेगा. Similarly, ये line के along इसका radius lie करेगा. And naturally, where they meet, that is the center of their circular paths, right? So that point, जिसका velocity 0 है, that point becomes your IOR. So this is step 1 and 2. Okay? And step 2 is if step 2 is step 3 talks about what will happen if they do not intersect, right? So we'll come to that. What happens if these lines do not intersect at a point, but they overlap completely? But this is step 1 and 2. In step 1 and 2 का एक example हम देखेंगे. So you can just copy that, and I'll give you an example. I think there's enough space though. So what we have over here is a rod of, what we have over here is a rod of mass M and length L. Okay? So whenever I write M comma, I'm just telling you its mass M and length L, and it's making an angle theta with the horizontal. This is actually a wall in the floor, and this rod is slipping. Okay, it's slipping, and तुम्हें इस point का velocity दिया है as V. Okay? So this point is moving down with the velocity of V, and I've highlighted this coordinate system. I want you to locate the IOR. Give me the coordinates of the IOR based on step 1 and 2. लाइंस ड्रॉ करके निकालना है. लोकेट द IAOR.
It would be outside the rod, right?
Yes, it can be outside the rod.
But it's at the point when it's when it's at contact with the wall. That's when we draw the perpendicular.
वापस बोल.
When we draw the perpendicular, the point could only be, if it's in the rod, it could only be at the point of contact with the wall and the rod, right? I'm saying if we draw the
Okay. Why do you say that? One rotation would cause it to go into the.
I'm saying like according to the steps, we have to draw the perpendicular, right?
Hmm.
And if it's in the rod, then the only point would be.
हाँ, okay, fine. हाँ, ठीक है. Just for the benefit of others, वो basically बोल रहा था कि अरे अभी perpendicular draw करेंगे ना, तो अगर rod पे होना है तो फिर मतलब एक तो इस line में होना है और rod पे होना है तो ये point पे होना पड़ेगा. That's what you're saying. Anyways, cool. So please follow both the steps and just figure out where it is. It's not very difficult. Rod का length दिया है, theta दिया है, इस instant पे कहाँ पे होगा? Chat. Continue. Sorry, Shiv, I just saw your message, but I think it was for something else. ठीक है, आगे से पढ़ता हूँ. Yeah, perfect. सही है. Nice. यार बाकी वहां से कॉपी मत करो. Just ये lines draw कर लो. Draw lines. अब if you see, this required two velocities to be given to you. मैंने एक ही दिया है. You think एक और पॉइंट का है कोई ऑब्वियस डायरेक्शन में वेलोसिटी? ये भी ध्यान दो कि वेलोसिटी निकालना नहीं है तुम्हें, बस डायरेक्शन चाहिए था.
Do you think the rod will move backwards as it falls downward?
Can it fall without moving backwards?
No, it can't.
हाँ.
So that should be the other.
Yes.
Okay.
सही है. Perfect. Right. So I think डिस्कस कर लें. तो बेसिकली ये पॉइंट you can then figure out कि अच्छा this is the other point जिसका obviously velocity का direction पता है. This has to slide along the floor if that's coming down. ठीक है. So with some other velocity, let's say with velocity u, you might have done questions in laws of motion where you find a relation between v and u, constraints से. But यहाँ पे इसका velocity u होगा, and what we'll do is we'll draw the lines perpendicular to these two. So ये एक line हो गया perpendicular to the velocity, ये एक line हो गया. So obviously that tells us कि this point is the instantaneous axis of rotation. ठीक है. And naturally उसका coordinates लिखने जाओगे तो this length is L cos theta, L sin theta. So it's located at, I think that yellow is too dim, located at L cos theta, L sin theta. All right. Now, before I go to a question on step 3, IAOR निकालने का एक advantage होता है, apart from the fact कि तुम आगे जो कुछ formula सीखने वाले हो, they will involve this axis. So we're going to learn some formulas maybe for kinetic energy or angular momentum, which will require you to know where this axis lies. तो वो तो है ही कि ये axis important है. But जैसे ये question में खुद they can ask you what is the omega of the rod. ये rod किस rate पे घूम रहा है, right? And there are two ways of solving it. I'll mention the other a little briefly, but like one very easy way of solving this is using the IAOR. Can you try and tell me what should be omega in this case?
V upon L cos theta.
Very nice. So IOR, just remember this is like the center of a circle. V दिया है तुम्हें, ठीक है? L theta वगैरह दिया है. So what is omega going to be? Maybe I can use a fresh. Okay. Alright. हाँ, तो ओमेगा क्या होगा? तो बेसिकली हमें पता था कि यार यहाँ पे इसका वेलोसिटी v है नीचे की तरफ, ठीक है? यहाँ पे अपना एक्सिस है, ठीक है? That is behaving as our center, ठीक है? So if that's the center of a circle and there is this point which is, अभी ये थीटा है, so this point is L cos theta distance away, तो इसका वेलोसिटी होना पड़ेगा रेडियस इनटू ओमेगा, तो v होना पड़ेगा L cos theta omega. So sometimes this is a neat trick to figure out what your angular velocity is. Okay, so omega is v by L cos theta. You can locate where the IOR is, and omega is going to be v by radius, velocity of any point by radius. But what is radius? Distance till the instantaneous axis of rotation. Okay. Okay. By the way, if I'm blocking your view, you're free to see it. Okay. All right. So
Excuse
now
me,
let's.
sir.
हाँ, बोल.
I have a doubt. So the
Ah.
distance of points on the rod with the axis of rotation, it
Ah.
won't be the same. So how can the IAOR be the center of a circle?
So all these points are performing circular motion about that point at this instant, but all these points can have different radii.
So they're performing circular motion, but not on the same circle.
Not on the same circle.
Just the same center.
With the same center, yeah. It's just like,
Okay, sir.
yeah, you got it. Right?
We can assume them to be concentric circular motion.
Yes, they're all concentric circles. So that's the definition of rotational motion. Rotational motion, body ka motion hai, jahan pe every point on the body is rotating about a fixed axis. Matlab every point of the body is performing circular motion, but un sari circles ka center lies along one particular axis. Right? So yahan pe in sare, they're all moving in concentric circles. Okay, अब step 3 से related क्या basically वहाँ पे why would we need step 3? So sometimes ऐसा हो सकता है कि okay, let's say कि इसका ऐसा velocity दिया है v by 2. So very easy one. इसका velocity दिया v by 2. Now we are asking you where the IAOR is, and as you try applying the steps, as you try drawing the perpendicular line, you notice कि यार दोनों के लिए जब तुम वो perpendicular line draw करोगे, velocity के perpendicular, the lines overlap. So you're not getting an intersection point, right? So what does that tell you? That tells you कि अच्छा ये intersection point मतलब ये radii हमने draw किया, कहीं ना कहीं यही line पे center lie करेगा. Now you just need to maybe apply logic or apply a little ratio proportion, we'll see, and you need to figure out where that particular center lies. कहाँ पे velocity 0 होगा.
At the center.
हाँ. So this is a very easy case. I hope you are able to see कि इस case में क्या बाकी को भी दिख रहा है IOR कहाँ पे lie कर रहा है? At the center. ठीक है? तो इस specific case में perfectly center पे lie कर रहा है. How do we locate that? Maybe just I'll एक तो इसमें तो दिख ही रहा है, but how do we prepare for maybe some other questions? तो एक तरीके ऐसा सोच सकते हो कि as we move along the radius, velocity linearly change होता है ना? As you move along the radius, v is r omega. r बढ़ाते जाओ, v बढ़ते जाएगा. तो linearly change होता है. तो you will see कि as you moving up, अगर यहाँ पे left v by 2 से right v by 2 हो रहा है, तो linearly gradually अपना ये जो velocity है वो कम होते जाएगा और फिर उस डायरेक्शन में बढ़ते जाएगा. right? So I'm just drawing the velocity vectors at different points. Okay, so if you imagine a diagram like this, you will see two similar triangles. Yape they are perfectly of the same size, but otherwise you'll see two similar triangles because they'll have the same angles. तो एक तरीका वो हो गया कि अरे यहाँ पे v/2 है, वहां पे v/2 है. लेंस का रेशियो, ये दो लेंस का रेशियो will be ये दो लेंस का रेशियो. So that's why we realize कि अरे ये लेंथ और ये लेंथ बराबर है. So you can use similar triangles, or you can use ratio proportion. You guys don't seem to have a difficulty with this one. I'll just label the IOR and I'll give you maybe some more examples. तो ये है अपना IOR. Okay. But before we move to the next one, क्या इसका ओमेगा क्या होगा? इस क्वेश्चन का? हाँ.
Where L is the length of the rod.
हाँ, L is the length of the rod. Say rod का length is L. ये दिया है. Can the others also see it's V/L? So imagine कि we are being asked to find omega. Okay. So again, one method is of course using the IAOR. Right. So if we use the IAOR, we can clearly see कि यार ये, let's say ये वाला point, वो वाला point का velocity v/2 है, उसका radius will be distance from the IAOR. तो उसका radius will be L/2. तो वहां से ओमेगा आ जाएगा v/L. So this is one way. Have any of you encountered any other way of finding angular velocity? नीचे वाले point और ऊपर वाले point का velocity दिया है. Any other method? नहीं? तो वो भी बता दे. तो वो भी काफी कुछ जगह पे यूजफुल होता है. So as I mentioned, the second method, maybe I'll introduce that concept or that formula, and this is basically how we find the angular velocity of one particle with respect to another particle. Yeah, let me explain हो क्या रहा है. In any question, they can tell you कि दो particle ऐसा randomly move कर रहे हैं, ठीक है? One is going like this, one is going like this. दो particle move कर रहे हैं. और वो दो particle के बीच में जो, let's say, let me just draw that. Let's say एक particle ऐसा move कर रहा है. This is particle A. Okay. So let's say this particle B, and let's say that's particle A. Okay. And they're not moving parallelly. Let's just say that their velocities are v1, v2, θ1, θ2 with the horizontal. Let's just say. Okay. Now these are two random particles. They're moving, and if you think about the line between them, the line between them could increase or decrease. Okay, based on these values and these angles, and on top of that, the line between them can rotate. So when they ask you omega of A with respect to B, वो basically पूछ क्या रहा है कि इनके बीच में जो line है, वो line किस rate पे rotate कर रहा है, उस line का omega क्या है, B के हिसाब से A उसके around कितने तेजी से घूम रहा है, ठीक है? So now ये जो मैंने diagram बनाया, this is in the ground frame. Okay, so what we can do is ground frame, ठीक है? Come on. Right. So what we can do is we can go to B's frame of reference because we want omega of A as seen by B. So it'll help to go to B's frame of reference.
So we'll resolve V1 into I cap and sigma.
Perfect, perfect. And then?
Then we'll use the relative velocity.
Perfect. Relative velocity use करेंगे. We'll resolve them फिर.
And then we know the distance between them. So we'll consider B as the point of IOR.
हाँ.
Case, and then we can find
Perfect, perfect. तो ठीक है. So basically अब क्या करेंगे? We'll go to B's frame. तो B के frame में I'm just getting to the ultimate thing. तो B के frame में we will observe some relative velocity. Okay, in B's frame, we will observe B to be at rest. इसका velocity 0 है, वो rest पे है B के frame में, but उसको A move होते हुए दिख रहा है. And you can subtract those vectors and all, and you can figure out कि A कैसे move कर रहा है. Let's say ultimately A is moving with this velocity. Is moving with a velocity VAB, velocity of A. Oh, come on. Velocity of A as seen by B. ये इतने velocity से move कर रहा है और ये angle theta है मान लो, ठीक है. And अब B के हिसाब से A का motion ऐसा दिख रहा है. Let's say this distance is RAB. So this is the distance between A and B. Okay, this is the distance between A and B. Now, if you think about this relative velocity is doing two things. इसका एक component इनके बीच में separation को change करेगा, right? इसका sin component, इसका ये line के along component B के हिसाब से A का जो भी इस direction में velocity होगा, that will be responsible for either increasing the separation or decreasing the separation, right? But it's this component which is actually responsible for A seeming to rotate around B, right? So which is the component responsible for rotation around B? It's this VAB cos theta. It's this perpendicular component, जो इस case में VAB cos theta है. So it's the component perpendicular to the line joining them. B के frame में omega जो दिखता है, okay, that will be omega of A as seen by B. That will be V perpendicular divided by distance between them. अच्छा, V perpendicular actually कौन सा? In fact, let me give some more clarity. ये relative velocity का perpendicular component upon distance between them. If I were to write it in words, ये भी अच्छे से लिखता हूँ. Omega of A as seen by B is relative velocity is component perpendicular to the line joining them. Sorry for my handwriting. Perpendicular to the line joining them divided by the distance between them. Is there any confusion? Just ask me. Relative velocity का perpendicular component upon the distance between them. And तुम्हारा बॉडी अगर रिजिड होता है ना, रिजिड का मतलब क्या होता है? रिजिड का डेफिनेशन क्या होता है?
That it's not elastic. When you apply force, it won't, like its shape won't change.
हाँ. And a very precise definition would basically be this कि उसके कोई भी दो पार्टिकल के बीच में separation change नहीं हो सकता है, ठीक है? So if this is part of a rigid body like this rod,
then there would be a force which would cancel the sin theta component. Like for VAB, there would be a force which should cancel this the sin theta component.
हाँ, so basically you're saying कि हाँ, you're basically saying कि sin theta component नहीं होगा. Perfect. So if this is a rigid body, ये वाला component होगा भी नहीं. ये component separation change करने के लिए है ना, VAB sin theta. तो अगर rigid body rod वगैरह है ना, you'll notice कि relative velocity will not even have that component. उसको सिर्फ एक घुमाने वाला component होगा. ठीक है? तो इस फॉर्मूला के हिसाब से इस क्वेश्चन का आंसर अगर ओमेगा में पूछ रहा था तो ओमेगा देखो क्या आएगा इस फॉर्मूला के हिसाब से. डज इट सीम टू एड अप like the question before I drew those purple lines was this?
So the velocity becomes v and the distance.
ये आगे जा रहा है v by 2 से, ये पीछे आ रहा है v by 2 से, right? So the moving in opposite directions. तो एक के हिसाब से दूसरे का स्पीड जो दिखेगा ज्यादा दिखेगा, दोनों का सम दिखेगा, right? तो क्या दिखेगा? relative velocity v दिखेगा, right? So according to that formula उधर भी देख सकते हो v by 2 plus v by 2, that becomes the relative velocity between these 2 points. and divided by distance between them was L. तो ये method से भी V by L आएगा. So both methods are this is actually quite important. So please remember that. That's like universal. कोई भी दो particle इधर उधर जा रहा है, can always use that method to find omega. Okay. A. Shiv, I'm just reading a chat. By the way, let me know if you type something in the chat. This was like 15 minutes ago. You type something, just bring it to my attention in case I don't read. Okay, you already asked the down. Okay, fine. Cool. चलो ये एग्जांपल बनता है एक आध और एग्जांपल देखते हैं. So I'll again give you a rod, I'll give you velocities, quickly locate the IOR and use any method you want to find omega. Okay, so this is your question. So let's say rod ऐसा है, ठीक है, इसका velocity 3v है, इसका velocity v है. Okay, rod का mass m है and length L है. Mass is of no use. ठीक है, length L है. Find omega and also find where the IOR lies. Cool. Yeah, find the IOR, locate the IOR, and find omega. Come on, jaldi.
Omega is equal to V by L.
Yeah, सही है.
Would the IOR be outside the body?
Yeah.
Yeah.
Because it will divide externally.
You figure out where it is, eh?
No.
अच्छा. नहीं, Shiv, you'll have to just check that. Remember, method क्या था? You could try drawing those vectors, right? So 3v से छोटा होते जा रहा है v. 3v से v हो गया, अब तक 0 आया नहीं है. तो बस figure out और कितना नीचे जाने में 0 आएगा.
Calculations are correct. It's L by below the lowest point.
सही है, शिव भी सही है.
L by 2 or L by 3?
Let's see. ठीक, L by 2 होगा. तो चलो देखते हैं इसमें क्या करना है. So we said कि हम स्टार्टिंग में तो ये परपेंडिकुलर लाइन ड्रॉ करेंगे और देखा कि यार दोनों के लिए परपेंडिकुलर लाइन सेम ही है. तो we don't know where the center is, we just know it's somewhere on this line. ठीक है. Now we want to figure out कि we want to find the point जिसका velocity 0 है and your velocity along this rod will change in a nice smooth manner. So you can see ये linearly जैसे नीचे जाओगे एक यूनिफॉर्म रेट पे कम होते जाएगा. ठीक है, माय डायग्राम इज डेफिनेटली नॉट गुड, बट 3v से वो यूनिफॉर्मली कम होते जाएगा. और यहाँ पे L डिस्टेंस नीचे आने में कितना कम हुआ है? 2v है ना. L डिस्टेंस नीचे आने में 2v कम हुआ है. कितना कम करना था स्टार्टिंग से? या ऐसा देखो, L डिस्टेंस नीचे आने में 2v कम हुआ है. 3v का v हो गया. यू वांटेड टू डिसअपियर, तो 2v कम हो गया है. कितना और नीचे जाने में कितना कम करना है अब एज ए कंटिन्यू गोइंग डाउन? परफेक्ट, राइट. v कम करना है, तो v कम करने के लिए और L/2 नीचे जाना पड़ेगा. ये थोड़ा रेशियो प्रोपोर्शन का खेल होगा. So that's where your IOR lies. Okay. So this is basically, it's like a rod. Imagine a rod is rotating about this point. और तुम्हें वो बस rod का ये part दिखाया नहीं है. So this is just maybe the top part of the top 2/3 part of the rod, which is rotating about this point. This point is behaving as the IOR at this instant. Here rod seems to be rotating about this. Cool. And तो ये आ गया IOR. ओमेगा कोई भी तरीके से निकाल सकते हो. या तो you can say omega is, if we use that method, relative velocity का perpendicular component by distance between them. So given, I mean, we don't even need to locate the IOR for that. Relative velocity 3v minus v हो गया. Sorry. And distance between them L हो गया. तो 2v by L is omega. ठीक है? या तो वैसा, या अगर तुमने निकाल ही दिया है IOR, तो omega is velocity of a point by radius as seen from the IOR. मतलब it's basically it's v by L/2. Anyways, so I hope you got the idea. All right, cool. Chalo. So let's move on and so I think sir taught you guys kinetic energy, right, of a rotating body. Cool. So let's maybe thoda slightly recap that, and with that transition to kinetic energy of, I believe what he didn't teach yet was rotating plus translating bodies. Okay, so just I'll put the heading in this manner: kinetic. Let's not use that. Heading down the kinetic energy of rigid bodies. ठीक है, हम in general है ना kinetic energy कैसे आता है देखेंगे.
Excuse me, so can you check the chat?
Okay, चलो why? हाँ. Let me just make a. So if you see his chat, sub page clear करेगा क्या? Let's just go with cancel. ठीक. Oh, come on. So if you just see the chat behind, his question is a very good one. He's saying, why is angular velocity, why is relative velocity, angular velocity the same as angular velocity with respect to IOR? अब ये please समझो, this is a very, very important concept. When a rigid body, let me just draw it and show you guys. So let's say I have a rigid body like this. Okay. Let's say ये point A है, ये point O है, ये point B है. Okay, so this is a rod rotating about, let's say the center. It's rotating about the center with some angular velocity. But let's say मैंने क्या किया, मैंने इसको 90 degrees center के about 90 degrees anti-clockwise घुमाया. तो इसका नया orientation हमें ऐसा दिखेगा. right? So this is the new orientation. So we see B at the top and we're going to see A at the bottom. Body को center के about rotate किया है. If I were to observe this motion from B's frame of reference, तो देखो B को क्या दिखेगा, है ना? B के हिसाब से O और A पहले उधर है. B is moving, but B के frame में क्या दिख रहा है? Now it's at the top, means somehow the rest of the rod is rotated and it has come below B. कितने से rotate हुआ है? 90. किस सेंस में? एंटी क्लॉकवाइज सेंस में. तो B के हिसाब से भी रॉड 90 डिग्रीज एंटी क्लॉकवाइज रोटेट हो रहा है. ट्राई सीइंग हाउ इट लुक्स लाइक विद रिस्पेक्ट टू A. A के फ्रेम में भी, है ना? तो A के फ्रेम में A पहले 90 डिग्री अबव, मतलब 90 डिग्री अगेन एंटी क्लॉकवाइज. A के हिसाब से O और B उधर था, अब O और B ऊपर आ गया, तो अगेन 90 डिग्रीज एंटी क्लॉकवाइज रोटेट हो रहा है. Take any other point on the rod, you will find कि यार उसके फ्रेम के हिसाब से रॉड उसके about 90 degrees anti-clockwise rotate हो रहा है. That tells you something for these rigid bodies कि you can take any point of the rod, angle rotated about that point is the same. Okay, and this is a very important point. इसके अच्छा अगर angle rotated same है तो omega, which is angle rotated by time taken, rate of change of angle, omega भी same होगा, alpha भी same होगा. Okay, so I'll make you write this. The point we are saying over here is omega is the same, omega of this body is the same with respect to every single axis on the body. Omega is the same, alpha is the same, which is why you'll never see us talk about omega about this axis or omega about the center of mass. Omega rod का ही property है.
So
So
this
rod
is for all rigid bodies, right?
for all rigid bodies. Okay? Rigid body का हर particle हर axis के about same angle से rotate करता है. हर particle, जैसे rod का हर particle इसके about 90 से rotate किया. Similarly, rod का हर particle कोई और particle के about भी अगर observe करोगे 90 से ही rotate करेगा. हर particle हर axis के about same angle से rotate करता है. So just write this. हाँ.
What if omega, like if this wasn't the case, they would separate, right?
If this wasn't the case, they would separate. Yes. एक ज्यादा angle rotate कर रहा है, एक कम rotate कर रहा है, they would separate. ठीक है, तो लिखो angle rotated, comma omega, comma alpha will be the same about every axis of a rigid body. Will be the same about every axis of a rigid body. Okay. You remember that. So that's why in this previous slide, that's why we were अपना हम relative omega, मतलब ये वाला टर्म तो B पे बैठ के उसका ओमेगा हमने ऑब्जर्व किया, दूसरा वाला हमने सेंटर एक्सिस सेंटर पे बैठ के ओमेगा ऑब्जर्व किया. कोई भी मेथड यूज कर लो, कोई भी पार्टिकल यूज कर लो, ओमेगा वही आएगा. ठीक है, हर पार्टिकल का हर एक्सिस के अबाउट ओमेगा सेम है व्हेन अ रिजिड बॉडी रोटेट्स. ऑलराइट, सो लेट्स मूव ऑन. वो हेडिंग लिख लो, काइनेटिक एनर्जी ऑफ अ रिजिड बॉडी. आई थिंक दैट वाज अ गुड क्वेश्चन. इट्स गुड टू have that cleared. Kinetic energy of a rigid body. Okay. All right. So just एक बार quickly we'll just see how this is derived. So imagine you have a rigid body. ठीक है? And imagine now we know कि there exists some point, it may be inside the body, maybe outside the body, but there's some point जिसके about the entire body seems to be rotating at this particular instant. So let's say that point is our IAOR. ठीक है? Now let's say there is a point, there's a particle on this body जिसका मास है mi, right? So like the first particle you can call as m1, second particle as m2. So I is just a way of labeling the ith particle. तो उसका मास है mi, उसका रेडियस है मान लो ri, okay? And ground के फ्रेम में उसका वेलोसिटी, remember this is the guy at rest, तो इसके हिसाब से जो वेलोसिटी दिखता है वो ग्राउंड के हिसाब से भी दिखता है, ठीक है? तो ग्राउंड के फ्रेम में इसका इस पार्टिकल का वेलोसिटी विल बी दिस डिस्टेंस इनटू ओमेगा, राइट? सो लेट्स से ओमेगा ऐसा है, सो इसका वेलोसिटी हो जाएगा आर आई ओमेगा, ओके, आर आई ओमेगा. Similarly, let's say our center of mass, you'll find that's another interesting guy. Center of mass, let's say कहीं पे तो है, ठीक है? Center of mass का distance RCM है, ठीक है? And RCM है, and let's say center of mass का velocity, फिर उस हिसाब से VCM हो जाएगा RCM omega. Okay. Now, kinetic energy of the body, the entire body. Yeah, there's no shortcut, direct shortcut at first to this. The way we understand kinetic energy of a particle is half mv square. So this body is a collection of particles. तो body का kinetic energy actually क्या होगा? सारे individual particles का kinetic energy का summation, sigma summation. सारे particles का kinetic energy जोड़ दो. तो हर पार्टिकल का काइनेटिक एनर्जी अब यहां से दिखेगा, इट्स सिंपली हाफ एम आई आर आई ओमेगा, राइट? आर आई ओमेगा इज द स्पीड. तो हर एक इंडिविजुअल पार्टिकल का ये काइनेटिक एनर्जी है, वो पूरा बॉडी के लिए ऐड करेंगे. नोटिस मैंने यहाँ पे ओमेगा आई नहीं लिखा, परफेक्ट, राइट? सो दैट्स व्हाई दिस so know your limits. अब एक मैंने एक फॉर्मूला दिया है, तो you should know कि when that is valid, right? This formula that we're going to write is valid for rigid bodies. Rigid bodies के लिए ओमेगा cm है ना? हाँ, because rigid body के लिए सेम है, ओमेगा स्क्वायर को बाहर रख सकते हैं, हाफ को भी बाहर निकाल सकते हैं, which will make this half summation mi ri square omega square. Okay, yeah. So for you guys, as you quickly go through the old lectures, you learn कि this is a term we deal with. It's called as the moment of inertia of a body. हर particle का mass into ये distance का square, ऐसा हर particle के लिए add करेंगे, तो we get something called as moment of inertia, जिसका symbol है I. And if you go through the old lectures, you'll see how based on this, you will learn to derive the moment of inertia of different shapes. Okay? So that's it for now. When we see this, this is not something that scares us. This is something, this ka formula we know for a lot of different shapes. Right? So that's just our moment of inertia. यहाँ से अब formula आ जाएगा. Kinetic energy is half I omega square. But now I want to be very specific. ये just because we are dealing with a couple of important points, and normally लोग को doubt आता है कि should I use ICM or should I use I about IAOR? इस case में, what do you think this moment of inertia is about which axis? Based on how we have derived things, ये कौन सा I होगा?
IAOR.
IAOR, very nice, huh? Because this RI is distance from the IAOR. तो इसके about निकाला गया है moment of inertia. So I would suggest just remembering it with that initial. Okay, so kinetic energy is half I about IOR omega square. A very important formula. Now, again, borrowing from something you guys have learned, there is a formula for relating I about this axis with I about the center of mass. एक formula होता है, ठीक है? वो formula है parallel axis theorem, जो बताता है कि I about any axis parallel to this guy will be ICM plus M distance square. ठीक है? So I about IOR is going to be ICM का सबसे कम होता है, ठीक है? Is going to be I about center of mass plus, perfect, right? And I've given this the name RCM square. So M RCM square. Now let's use this. Yeah, that's your parallel axis theorem. Let's use that. Let's plug that in over here and let's see what we get. Kinetic energy, first term ICM omega square. Second term perfect. So here half mRCM whole square omega square.
So it's in the form of rotational kinetic energy plus translation kinetic energy.
Perfect. क्योंकि ये जो RCM
RCM omega is velocity
perfect.
of CM.
Perfect. So RCM omega is velocity of the center of mass. So now our kinetic energy looks like this. Now, so ICM omega square plus half mv cm square. I'll talk about these two terms. They have special names as well. But I just want you to notice this derivation and realize that both formulas are actually the same. ये नहीं है कि ये एक केस के लिए वैलिड है और वो एक अलग केस के लिए वैलिड है. ठीक है, ये नहीं है कि ये सिर्फ रोटेशन के लिए वैलिड है और वो रोटेशन प्लस ट्रांसलेशन के लिए वैलिड है. ऐसा नहीं है. Yes, perfect. So these are actually valid for any rigid body. Okay, you can use either of them. It's up to you what you want to use. Now this is the advantage. There's only one term here. So if you know where the IAOR lies, and if you know to calculate moment of inertia about it, use this. For example, हमने पहले तो example देना देखा एक rod rotating about a hinge. मस्त उधर ही IAOR है. एक formula होता है rod का end के about moment of inertia. So you know that already. You will use this for kinetic energy. Yeah, एक pure rolling disc, pure rolling body. जो आज हमने बात किया कि kinetic उसका IAOR नीचे होता है, right? So again we know that उसके about moment of inertia निकाला जा सकता है. We could use this. When you don't know where the IAOR is, and you, like we saw in some examples, if you think it's going to take some time to figure out where it is, मत use करो, सीधा है ना ये result use कर लो. Okay, so it's but realize that both are the same. Both can be used in any case as long as it's a rigid body, which it will be. इसके specific नाम होता है. So this guy is called as now these are just labels, okay? Because this seems to be the kinetic energy the body would have if it's only rotating about the center of mass.
Because VCM would be 0.
Because VCM would be 0. अगर बॉडी सेंटर ऑफ मास को पकड़ के रखेंगे और उसके अबाउट ही घुमाएंगे तो ये काइनेटिक एनर्जी दिखेगा. तो इसको नाम देते हैं रोटेशनल काइनेटिक एनर्जी. सेंटर ऑफ मास नहीं हिला रहे हो, बस घुमा रहे हो. Okay, so therefore the name rotational kinetic energy. This is just a label. When they ask this in a question, you should know what it refers to. The other one, उसमें ओमेगा 0 है, मान लो ओमेगा घुमाया ही नहीं और हाँ, so it's only moving, it's only translating. So that's where that term comes. तो इसलिए इसका नाम है translational kinetic energy. See, so be aware of those labels. And of course, their combination of this term over here is total K. So let's just practice. I was looking for the duster. ये हो गया क्या लिख के? Done? Cool. So जल्दी से कुछ practice कर लेते हैं. I mean, you guys won't know the formulas, so let's see what can be done. But let's just, you learn the formula. So let's say I have a rod like this. काफी often ये use होता है. Rod is rotating about a hinge. Rod, ठीक है, हर बार uniform rod ही draw करूंगा मैं. I may not mention. So it's a uniform rod, a mass m, length L, and is rotating about this hinge with an angular velocity of omega at this particular instant. And I want the kinetic energy of the rod. Very simple. So क्या होगा? Those who know the formula will be able to answer, but you guys will learn the formula soon. As a recap for those who don't know the formula. So,
We'll use I for rod is ml square by 12.
okay, but what will your answer be?
ml square omega square by 24.
हाँ, ठीक है. देखिए अब तूने क्या किया? ml square by 12 ये अपना rod है, ठीक है. For the others who don't know the formula, rod का center के about ml square by 12 होता है, right?
I confused them.
हाँ.
It's ml square by 3.
हाँ, cool. तो rod का center के about ml square by 12 होता है. Rod का end के about
ml square by 3.
ml square by 3 होता है. ठीक है. There's a simple derivation for this, but these are going to be things you're going to memorize either way. ml square by 3 कैसा आता है? ml square by 12 plus parallel axis theorem. तो plus ml by 2 whole square अभी देखा था, है ना? तो ml square by 12 plus ml by 2 whole square adds up to ml square by 3. ठीक है. तो rod का वैसे कोई भी एक्सिस के ऊपर अभी निकाल सकते हैं, but these are two which we're going to specifically remember. Center के about by 12, end के about by 3. Alright, so I hope now you know why the ml square by 12 वाला formula was wrong, because the answer you gave then was half I cm omega square. If you use that, you also have to add half m vcm square to that. Okay? So, but when we already know I about the hinge, I about the IOR, when we know that, then there's no point, you know, taking a little extra time and writing two terms. Since
ml square by 3
perfect,
and 2 omega.
perfect, right? So since we know this guy, हम वो वाला use करेंगे. ये बहुत easy होता है यार kinetic energy लिखना. Whatever, ml square by 6 omega square. थोड़ा और examples दिखेंगे. So I think this was along the lines of what sir had done, only pure rotation. Let's take the example of pure rolling. Okay, like you get certain results for pure rolling. Let's just see that. So I'll again give you guys the formula for that, pure rolling ka, but let me just give you the question. So imagine you have pure rolling objects. This is the scene. Okay, this is the scene. I am giving you mass of the body. I'm giving you the radius. Okay, and I'm giving you velocity of the center of mass. Okay, VCM दिया है. I'm not giving you omega, but VCM से omega आ जाएगा, है ना? VCM is R omega. ठीक है. So ये scene है. This could be right. So what I want you to find is find the kinetic energy. ये देखिए kinetic energy. Right? मतलब अगर rotational के chapter के पहले, if you would have asked this question, your guess would have been half mv square, half mvcm square. But now we know a little better. Okay, that is not the complete formula. Half mvcm square एक term है ना? Complete formula थोड़ा अलग है. So question is find the kinetic energy and if the object shown is a pure rolling. Okay. So for our reference, ये results देख लेते क्या है. So if the object is a pure rolling, first one is a ring. Okay. Disc, ring और disc में फर्क क्या है? Ring is just the boundary. Otherwise, you can't put your fingers through it. Right? Ring is just the boundary. Disc is one plate-like object. Okay.
The first blanket would be MPG and the one.
Ah, very nice, very fast. Good. This guy is a hollow sphere. Move on if you've gotten move on. Just for the benefit of others, एक बार मैं formula बता देता हूँ. And the fourth one is a solid sphere. ठीक है? तो जिनको आता है formula start कर लो. For the newer guys, I'll just tell you कि for a ring, और भी results है, so I would suggest watching those moment of inertia lectures. पर ring के लिए इस axis के about moment of inertia होता है mr square for a ring. ठीक है? इस axis के about, center के about. For a disc होता है mr square by 2. For a so subtle changes, सब में mr square है, it's only that ratio, that number in front of it which changes. और eventually यार सवाल कर करके ये सब याद भी हो जाएगा. Hollow sphere के लिए the formula is about the center 2/3 mr square. ठीक है? About the axis. In fact, hollow sphere though, it's basically about any line passing through the center. They're all symmetrical. So about the diameter is 2/3 mr square. And solid sphere का 2/5. Those who know this, please move on. Just सभी का निकाल के रखो. 2/5. कैसे मिटाया यार उसे? Two by 5. ठीक है? Last one. And just for your benefit again, you also have at your disposal parallel axis theorem जो बोलता है I about any axis, like just in case you need I about the lowest point, LP, lowest point. So I about any axis is ICM. Okay, this has to be ICM plus M distance square. Right? So that's at your disposal. This is just for the newer guys. So I about the lowest point is ICM plus M R square. हाँ, किसी का बाकी है? You done, Kim, with all 4? Nice. Anyone else done with the first one? ठीक है, तो let's see. ठीक है, अगर pure rolling ring, again I'm looking for the duster. अगर pure rolling ring है तो so अच्छा, for any of those objects, by the way, before we even look at the result, we could have applied either of the formula, या तो half ICM omega square plus half m VCM square, या half I about IOR omega square. But since this is pure rolling, do we know where the IOR lies? It's a good question to ask before you write kinetic energy. At the lowest point, we saw this earlier today. So our IOR is over here. And if you think about it, it's easy to find moment of inertia about that axis. So why not try to straight away use this formula? So half I about the IAOR omega square. ठीक है, सीधा ये lowest point के बाद लिखता है. अब इसमें was what was or what won't be mentioned in the question, but what you can figure out is VCM is R omega, right? So if you need omega, you could write omega in terms of VCM. Starting with the ring. Okay, अब ring के लिए moment of inertia of the center of mass के about it's mr square, right? So what is moment of inertia about that lowest point? mr square plus mr square. ठीक है, that's how moment of inertia works. Center of mass के about पता है तो जानो कि more or less बाकी axis के about निकाल सकते हैं mr square plus mr square. Okay, ICM plus m distance square. So that makes moment of inertia 2mr square, and that makes your kinetic energy half 2mr square omega square. See? Great. So that makes the answer mr square omega square. And just note कि अब सवाल ने ओमेगा नहीं दिया था तो मोस्ट लाइकली आंसर भी उसके टर्म्स में नहीं होगा, जो दिया है उसके टर्म्स में होगा. तो इन टर्म्स ऑफ VCM can again substitute that r omega is VCM. So m VCM square हो गया. ठीक है, got it? Did everyone get this? Notice कि अब है ना, it's similar to a translating body. सिर्फ translating body में half m VCM square होता है. अब ये रिंग जब रोल हो रहा है, just that formula is different. Again depends on velocity का square, depends on mass. बस half की जगह is just m VCM square. Okay, so like that in an exam you would, this may just even be a part of the question. Okay, you would need to be able to quickly find the kinetic energy of any pure rolling body. So to save time, we've already seen this, you can just work it out with me. Disk के लिए moment of inertia about the IAOR, ये तो मैं लिख रहा हूँ कुछ time बाद. As you practice moment of inertia, you won't even need to think much. Disk के लिए center के about mr square by 2, mr square जोड़ दो तो ये हो जाएगा 3/2 mr square. Center के about half, वो याद करना है, plus mr square 3/2 mr square. So that makes your kinetic energy half into 3/2 mr square into omega square, right? So that makes it 3/4 m VCM square. Again, a slightly different formula. वो disk के लिए हो गया. You don't need to remember this. ठीक है? You just need to remember ICM क्या है और basic funda kinetic energy का formula concept क्या है. With that, you can get these results. Hollow sphere, you can work ahead even as I'm writing. Hollow sphere के लिए kinetic energy again will be half moment of inertia center के about 2/3 plus mr square adds up to 5/3. And again what we'll do is 5/3 into 2 हो जाएगा 5/6, right? एंड आर स्क्वायर ओमेगा स्क्वायर हो जाएगा VCM स्क्वायर, ठीक है। एंड द लास्ट वन इज सॉलिड स्फीयर, ठीक, सॉलिड स्फीयर का 2/5 सेंटर के अबाउट, तो क्या होगा बाकी बताएं, बताओ। 2/5, लेट्स वर्क थ्रू इट, इवन ओरली कर सकते हैं। 2/5 सेंटर के अबाउट, लोएस्ट पॉइंट के अबाउट कितना, 7/5, हाँ, एंड देन ओवरऑल 7/10, great, so you all got it, okay, so half into 7/5, all right. Now this may later on just be a part of a bigger question. The way you have solved work energy theorem के questions, कोई हिल से एक ऑब्जेक्ट को रिलीज किया, ऑब्जेक्ट जब नीचे आया तो वेलोसिटी कितना होगा, कंजर्वेशन ऑफ मैकेनिकल एनर्जी, पोटेंशियल एनर्जी कम हुआ mgh से तो काइनेटिक एनर्जी उतने से बढ़ गया, तो हाफ mv स्क्वायर इज mgh, ये लगाते हो ना। इसमें बस फर्क क्या होगा, दे कैन गिव द सेम क्वेश्चन वेयर इंस्टेड ऑफ अ ट्रांसलेटिंग बॉडी इट कुड बी अ रोलिंग हॉलो स्फीयर। रोलिंग हॉलो स्फीयर को एक इंक्लाइन से, लेट्स ट्राई दैट, रोलिंग हॉलो स्फीयर को एक इंक्लाइन से रिलीज किया, नीचे आते आते रोलिंग हॉलो स्फीयर का क्या वेलोसिटी होगा, राइट। एंड again I'm searching for the
that case the total kinetic energy would increase, right? So that means the rotational part and the translation part will increase by the same, like if the total kinetic energy increases because of work energy theorem,
ठीक है,
rotational part and the velocity part would have the equal
why, क्यों सेम अमाउंट से क्यों इंक्रीज होना चाहिए,
because of formula, right?
depends on what you're doing with it, right? I could easily rotate, yeah, I could rotate a fan without making its center move,
Okay, yeah.
है ना। So and again that's why I showed you that derivation. So don't think of those two as like separate parts that kinetic energy is made up of. It's just a label. If they ask you,
Okay, so if the total kinetic energy increases, we know that, but then how could we figure that how much of that extra energy goes where?
so the good thing is I understand तू क्यों confuse हो रहा है। You're saying total kinetic energy जब बढ़ रहा है तो मेरे साथ इधर दो टर्म है, हाफ ICM ओमेगा स्क्वायर एक टर्म है, हाफ MVCM स्क्वायर एक टर्म है, कैसा पता चलेगा कि यार कौन क्या किधर वो इंक्रीज इन एनर्जी कहाँ जा रहा है। गुड थिंग इज आई एम टॉकिंग अबाउट प्योर रोलिंग वाले केसेस, प्योर रोलिंग में दे आर नॉट इंडिपेंडेंट, V is dependent on omega, तो जो उनमें से एक टर्म जिसमें V half m VCM square है, like just to show you what this would have looked like had I applied let's see this over here. Alternatively इसको कैसे लिख सकते थे, half ICM omega square, तो एक 2/5 m r square omega square आता था, right, and एक half m VCM square आता था, but notice कि यार these are both are dependent
on VCM.
both are dependent on VCM. Omega and VCM are interrelated, so R omega is replaced, will again depend on VCM. R omega becomes VCM.
Okay, that's what I meant when like it's increasing, then VCM would increase by the same thing, so both of them would scale by the same value, right? Because if VCM is constant,
हाँ, they'll increase proportionally.
yeah, that's what I meant.
अगर जब ये terms लिखोगे ना, तो ये terms का एक just right now you could derive, you could
Value for both. VCM is a constant value for both the energy.
perfect.
So it keeps on increasing for both of the.
Perfect. So VCM is common. If you, like in this case, what is the ratio of, if I ask you ratio of rotational kinetic energy to the translational kinetic energy?
So 1:5 is to 1. 1/5 is to 1/2. It's just 2/5.
हाँ, 2/5.
1/5 is to 1/2.
1/5 is to 1/2. So 2/5. So this ratio is like fixed. This ratio depends on ICM. That's it, right? तो हमेशा ये उसी रेशियो में बढ़ेगा, उसी रेशियो में बढ़ेगा। potential energy कम हो रहा है, तो 2/7 of that will go in rotational kinetic energy, 5/7 will go in translational kinetic energy. ठीक है? तो एक question कर लो. So you have these results. You could use these results for the, again, I'm searching for the rest. You could use these results. Imagine you don't have to derive them again. Answer this question. Okay. So, a disk, ring, I mean, all four of those contenders, HS is hollow sphere and SS is solid sphere, are released from the top of a smooth track. नहीं, smooth नहीं. From the top of a track of height h. Okay. Height h. I'll draw the diagram. Height h. There is sufficient friction. There is sufficient friction to ensure pure rolling. See? You can't have this pure rolling thing in a smooth road. You do need friction.
Or else the body won't move ahead.
नहीं, so if imagine अगर, so this is my diagram and यहाँ से अपना start हो रहा है, ठीक है, उन चारों का रेस start हो रहा है. Question मैंने लिखा नहीं है.
Maybe is it because it will move only translate?
Perfect. So
It won't roll.
if there's no friction, it will only translate. घुमाने के लिए तो friction चाहिए. ठीक है? Friction अब आगे भी सीखेंगे कितना friction आता है, कितना उसका value होता है based on angle, वो सब सीखेंगे. हाँ. So but it will be static friction. ठीक है? There will be static friction to ensure कि यार ये proportionately, मतलब V बढ़ रहा है तो proportionately omega भी बढ़ रहा है. सब आगे देखेंगे. Right now this only depends on your work energy theorem. The question is this: they're all released from a height h. In what order will they reach the bottom? Like how will they finish the race? कौन first आएगा, कौन second आएगा? That's your question. It's so much easier. In what order will they reach the bottom? Shiv, I'm just seeing your results. यार almost सही था. Just एक दो term check कर ले if they need to be interchanged.
Oh, I got that.
Like
Very nice.
I formed the formula which takes
Where x is that ratio, is it?
x is the extra energy, c is the constant. So depending on the c,
okay,
I
perfect.
can find.
Very nice.
And I found c.
So
4 would be
okay,
here.
got it.
Um,
Is that how it is?
Yeah.
Oh, यहाँ से उठा रहा है तो
हाँ.
okay, okay.
So it's the same order. So 1, 4 would be solid sphere, then ring, then hollow sphere, and then
Yeah. शिव ऐसा तेरा सही है, बस only 2 terms need to be changed, interchanged. बाकी के लिए एक हिंट दे देता हूँ. So I just say कि you know the formulas, right, for kinetic energy, like based on whatever this object is, you know कि kinetic energy could be written as some constant, right? So there was always an mvcm square. So for the time being, just in general, you can write that kinetic energy as some constant into mvcm square. ठीक है? और अब work energy theorem लगाओ. Decrease in potential energy is increase in kinetic energy, and you're starting from rest. I don't know if I mentioned that, but release from the top, right? So starting में K is 0.
Sphere, hollow sphere, disk, and ring.
Is that the order?
Yeah. Sphere, hollow sphere, disk, and the ring.
इसने भी वही बताया, थोड़ा almost close है.
Last वाला interchange करना है, मतलब ring and disk.
Hollow sphere and disk.
Okay, yeah.
Good, nice. तो इसमें जिनको आ रहा है यू कैन कंटिन्यू, बट एक चीज बता देता हूँ कि यहाँ पे द फ्रिक्शन इज स्टैटिक. ओके, एंड अगेन ये पॉइंट भी बाद में भी देखेंगे प्योर रोलिंग का, बट प्योर रोलिंग में रिमेंबर वी सेड द लोवेस्ट पॉइंट डज नॉट स्लिप, राइट? सो दिस इज अ केस ऑफ स्टैटिक फ्रिक्शन. ओके, एंड इन दिस स्पेसिफिक केस
We can take
हाँ, मतलब इन दिस स्टैटिक फ्रिक्शन है, मतलब फोर्स लग रहा है पर वो वर्क
only initially. Like it's only occurring at the initial point, and it's moving there.
नहीं, इट्स डेफिनेटली अकरिंग इवन व्हाइल मूविंग. ठीक है, इट इज अकरिंग व्हाइल मूविंग, बट यहाँ पे लेट्स से ऐसा फ्रिक्शन एक्ट कर रहा है. ठीक है, ये पॉइंट का वेलोसिटी 0 है. मतलब व्हाइल फ्रिक्शन इज एक्टिंग ऑन दैट गाय, व्हाट इज द डेफिनेशन, हाउ डू यू फाइंड वर्क डन? फोर्स इनटू डिस्प्लेसमेंट ऑफ द पॉइंट जहां पे फोर्स लग रहा है. सो नॉट द सेंटर ऑफ मास, पॉइंट जहां पे फोर्स लग रहा है. तो जिस पार्टिकल पे फ्रिक्शन एक्ट कर रहा है वो पार्टिकल हिल नहीं रहा है till that particle lifts off and the next guy comes down, right? तो इसमें क्या होता है, friction is not doing any work. ठीक है, work done by friction in pure rolling is 0. Work is friction का dot product with the displacement of the point of application of the force. So इस केस में work done by friction is 0 in this case in pure rolling, and I'll mention this again later as well. But friction basically work नहीं कर रहा है, which is a good thing. तब हम बोल सकते हैं कि mechanical energy is conserved. मतलब nobody else is involved. यही simple सा कहानी है कि अपना gravitational potential energy कम हो रहा है and kinetic energy accordingly बढ़ रहा है. ठीक है, तो जितने से gravitational potential energy कम हो रहा है उतने से अपना kinetic energy बढ़ रहा है. Decrease in gravitational potential energy is increase in kinetic energy. Decrease in gravitational potential energy, very straightforward. mg, height descended by the center of mass. Okay? And height descended, the small guys, height descended by the center of mass is roughly, basically it's h. So mg h नीचे जाने पे, center of mass h distance नीचे जाने पे इतने से potential energy कम हुआ. That's available for this guy to pick up. काइनेटिक एनर्जी कितने से बढ़ा, पहले 0 था, बाद में शिट व्हाई डिड आई रिमूव दैट, हाँ बाद में सम कांस्टेंट इनटू mvcm स्क्वायर, राइट? तो इंक्रीज इन काइनेटिक एनर्जी इज सम कांस्टेंट इनटू mvcm स्क्वायर, और इनिशियली 0 था, सो दैट्स द चेंज इन काइनेटिक एनर्जी. तो आई मीन आई एम जस्ट शोइंग कि वैसे तो कंपेयर तुम थोड़ा लॉजिकली भी सोच के कर सकते हो विदाउट फाइंडिंग द एक्चुअल वैल्यू, बट कभी कभी हो सकता है ये एक मैट्रिक्स मैच वाला सवाल है जिसमें ये दिया है और पूछा है चलो मैच कर लो, रिंग का क्या वेलोसिटी होगा नीचे जाने पे, डिस्क का क्या होगा नीचे जाने पे. तो अगर प्योरली रिंग होता
So what
सिर्फ,
is
हाँ
so what is C in this equation?
व्हाट इज
C.
so C is that constant. जैसे so let me complete what I was saying. Let's say डिस्क का ही समान होता, then डिस्क के लिए do you see कि यहाँ पे 3/4 था, थ्री बाई फोर था, है ना?
Yes, sir.
हाँ, तो if the question was only find final velocity for a disk, I would have used this. But just let's say it's a matrix match question and they're asking you final velocities for all of them. So you're not it wouldn't be a good idea to sit and solve the same thing again and again for all four, when you can see that the only thing that differs is k का फॉर्मूला में बस वो नंबर वेरी कर रहा है, इधर 1 है, उधर 5/6 है, इधर 7/10 है, इधर 3/4 है, तो ओनली वो नंबर चेंज हो रहा है, that's it, right? So a good idea in those questions would be to just take the kinetic energy as some constant into mvcm square and find the answer. तो यहाँ पे vcm basically आ रहा है root gh/c. Now typically translating body के लिए वो c half होता है, you're used to half mvcm square, that's why you normally get a result of root 2 gh in those cases, right? कोई भी बॉल को h हाइट से ड्रॉप करो, h हाइट नीचे जाने पे उसका स्पीड रूट 2 gh होता है काइनेमैटिक्स में, ठीक है? क्यों? बिकॉज दैट टर्म इज नॉर्मली हाफ. अब यहाँ पे देयर आर डिफरेंट टर्म्स. यहाँ पे फॉर जस्ट पुटिंग द वैल्यूज, रिंग के लिए c is 1, राइट? एंड देन जस्ट आई एम ट्राइंग टू राइट इन डिसेंडिंग ऑर्डर. 1 के बाद आई थिंक वो अपना होलो स्फीयर आएगा जिसके लिए c was 5/6. Then 7/10 के पहले वो डिस्क, हाँ 3/4, because 3/4 is 7.5 and हाँ 0.7 and solid sphere का 7/10 0.7, ठीक है? 7/10. तो you can see कि जिसका c सबसे बड़ा होगा उसका v सबसे कम होगा. So therefore the answer for this is velocity same height नीचे आने पे always this guy जिसका c कम है उसका velocity सबसे ज्यादा है. So solid sphere at any given height below the top, solid sphere will always pass through that point with the greatest velocity. Imagine यहाँ पे एक check point है, तो मैं हमेशा दिखेगा कि उस check point से solid sphere सबसे तेजी से पास कर रहा है, right? उसके बाद फिर disk, उसके बाद hollow sphere, उसके बाद ring. So because at every point below the top, the solid sphere has the greatest speed while crossing to that point, it will also be the first guy to reach the bottom. Okay, so SS comes first, and then so on and so forth. You have disk, then you have hollow sphere, then you have ring. Cool. All right, so that was your work energy theorem. I think just see. Yeah. चलो एक और क्वेश्चन करेंगे and then maybe we can just take a break. I think काफी लंबा लेक्चर है ना आज, but everyone's understanding अब तक जो भी हुआ है all good. एक आध you done?
Yeah.
Okay. एक क्लास just to see है ना फॉर्मूला अंदर मन में बैठ गया का. तो let's say कि I have a simple one, hollow sphere ले रहा हूँ and let's say यहाँ पे मेरा hollow sphere है, ठीक है? let's say यहाँ पे एक प्लेटफॉर्म है ऊपर, ठीक है? और यहाँ पे भी एक प्लेटफॉर्म है नीचे. एंड लेट्स से ऊपर वाले प्लेटफॉर्म का वेलोसिटी इज 4 meters per second. नीचे वाले प्लेटफॉर्म का वेलोसिटी इज 2 meters per second. Okay. Again, if these are smooth, then they will move and this guy will not rotate. ठीक है. Thing is, they're not smooth. So there is enough friction to ensure that यहाँ पे कोई slipping नहीं हो रहा है और यहाँ पे कोई slipping नहीं हो रहा है. Okay. So enough friction to ensure there's no slipping. Friction to ensure no slipping. Okay, and I want you to find the kinetic energy. So find find the kinetic energy of the hollow sphere. उसका mass is 3, radius is 1. SI units में सब कुछ है.
So that's the test for the ring.
This is HS hollow sphere. Uniform hollow sphere. Think about the formula, right? So think about the terms in that. So you want to find that first. So you need BCM and you need omega. और इतना बता देता हूँ, like ensure no slipping basically means कि यार ये जो है ये वाला इसके साथ साथ जा रहा है. If they were not moving in the same velocity तब कुछ slipping होता है. So there's no slipping between them. ये साथ साथ 2 के स्पीड से जा रहा है और वो साथ साथ 4 के स्पीड से जा रहा है.
So should it move in the rightward direction with the velocity of 2 meters per second?
You're close, but any changes?
6. Is it 6?
The velocity?
Yeah.
6 नहीं होगा. I mean, you can imagine that drawing, right? So you can definitely.
The upper surface is going to push it in this direction,
हाँ.
and the lower one will push it in the other direction.
So this is what those two are doing. That is making इसका velocity 4, इसका 2. That's it.
Yeah.
Abhi somewhere between these 2 points, your velocity changes direction. Somewhere your velocity is becoming 0, it changes direction. But don't you think यार center पे तो
We just need to find.
somewhere between 4 and 2 होगा ना, 6 नहीं होगा. हाँ बोल.
Yeah, I was saying if we can directly find omega, we can find the velocity of center of mass. from the
Yes.
Perspective of that 2 meters per second.
Yes, you can do that.
I got the answer that.
क्या आ रहा है
I got 45 by 8.
पूरा मिलके?
Yeah.
देखा एक बार. ओमेगा एटलीस्ट निकाल दो. कमान ओमेगा पता है ना.
Yeah, 3.
Hmm.
Omega is equal to 3.
और तो यहाँ पे एक what is this? Where is this 5/6 coming from?
From your 5/6, like from this perspective, I was. So then, like, no slipping point.
So you're writing half I about this point.
Yeah, MR square into VCM.
Okay, firstly that would be omega square.
Yeah.
Moreover, and that's it. That's you're just writing this term, right? No other term.
Yeah.
So the thing is, this is not the I over. Oh, rest में नहीं है.
But from the ground.
From उसके frame. हाँ, but मुझे ground के frame में फिर kinetic energy चाहिए.
अच्छा. Okay.
So VCM का एक simple hint दे देता हूँ. यार VCM आंसर नहीं है. VCM तुमने फर्स्ट टाइम कैसे बोला था? Remember that question I gave you today? तुमने कैसे बोला था कि यार सेंटर पे 0 होगा?
Yeah, sorry.
What was your hunch? There was some hunch behind you guys saying कि यार ये rod तो इसके about center के about घूम रहा है.
At such center, the distance between the 2 points would be same and their velocity would be same.
Okay.
So like their product would be.
Okay. तो एक चीज बता देता हूँ यार, सेंटर का जो वेलोसिटी होगा ना, that'll be the average of these two. Think about it. Center का velocity you can prove using vectors as well, but it's basically going to be the average of these two. For instance, like क्यों होगा? क्योंकि सेंटर का जो भी वेलोसिटी हो ना, सेंटर का जो भी वेलोसिटी हो, मान लो सेंटर का वेलोसिटी VCM है और ये बॉडी ऐसा ओमेगा से रोटेट कर रहा है, ऊपर वाले का VCM से कुछ अमाउंट ज्यादा है तो नीचे वाले का VCM सेंटर के साथ, देखो VCM आगे बट सेंटर के रिस्पेक्ट में R ओमेगा पीछे, तो ये लोएस्ट पॉइंट का VCM माइनस R ओमेगा, राइट? तो इफ यू कैन सी सेंटर से ऊपर जाते वक्त जितना वेलोसिटी बढ़ा, नीचे आते वक्त उतना ही वेलोसिटी घटा, राइट? सो the center will actually end up being like, इनका वापस एवरेज ले लो यार, add them up and divide by 2, you get VCM. So center का velocity will always be the average of the velocities at the two ends. That's a neat trick. Could do what he was also saying, first find omega. Omega के लिए मैंने आज formula दिया, so omega निकालना. You could do that, but there's also very simple, it's bound to be the average of those two. So omega निकाल दो, VCM निकाल दो, and then just apply this formula. All right, so K is, I'll let you guys do this one, half I. So इसमें just notice कि IAOR lowest point इस बार नहीं है. Simple, you have to ask yourself, यार ये हिल रहा है या नहीं हिल रहा है? हिल रहा है, तो ये IOR नहीं है. IOR कहीं ना कहीं बीच में होगा. एक तो उसको locate करो, फिर I निकालो, that's a little waste of time. So best is to use the second formula. Use this. Find VCM like I just said, and find omega, and then देखो क्या आ रहा है. मिड पॉइंट का वेलोसिटी हमेशा ना एंड्स का एवरेज होगा. तुमने आई थिंक 10th कोऑर्डिनेट ज्योमेट्री में सीखा था, मिड पॉइंट का x कोऑर्डिनेट इज x1 + x2/2, y कोऑर्डिनेट इज y1 + y2/2, है ना? तो कोऑर्डिनेट्स ही एवरेज है, तो कोऑर्डिनेट्स को डिफरेंशिएट करो विद टाइम dx/dt, वेलोसिटी भी एवरेज ही आएगा. सो इट्स द एवरेज ऑफ दीस टू, जस्ट ऐड देम एंड डिवाइड बाय 2, मिड पॉइंट का वेलोसिटी आएगा. क्या ओमेगा 3 आ रहा है? ओमेगा 3 आ रहा है. VCM 4 - 2, 2 का आधा 1 आ रहा है. 1 आ रहा है. Cool. So अच्छा, so मतलब आंसर शायद you're all almost there. Okay, so ओमेगा अपना फॉर्मूला है V average, the one we saw today, का नहीं V average नहीं, V relative का perpendicular component upon distance, ठीक है, between them. So relative upon distance. Okay, so V relative, if you see, is going to be 4 and 2 का relative velocity is 6 and is already perpendicular to the line joining the two of them. Again, 4 + 2 is 6 and divided by the distance between them. So distance between them is actually 2r, है ना? हाँ, 1 and 1 and 1, 2, right? So that becomes 6. That becomes 6 by 2. That becomes 3. So your relative angular velocity is 3 radians per second. Omega aa gaya. That's going to go over here. Remember, it's the same about every frame. ये तो इस पे बैठ के देखा वो center के भी उतना ही आएगा. VCM के लिए, so I'll just say कि velocity of midpoint is, maybe I'll just write it this way, V1 plus V2 by 2. So just to show you कि अगर यहाँ पे V1 है और यहाँ पे V2 है, और ये point उनका midpoint है, midpoint, तो velocity of the midpoint कोई भी rigid body के लिए is going to be ऐसा V1 plus V2 by 2. So over here, velocity of the center of mass, if I take forward as positive, 4 plus minus 2 by 2. So this becomes 1 meter per second towards the right. Okay? Let's plug it over here. You have your answer. So that first term, the rotational kinetic energy, is half I about center of mass, which is, this is what? This is a hollow sphere. So we'll go with 2 by 3 mr square. M is 1. Or is it 3? 3. 2 by 5, 2 by 3, m, r is 1 square. So half I omega square, omega is 3, plus half m VCM square. VCM is 1. So you can see this is 1.5 and that is ye sab cut ke 9, 10.5.
So can you explain the velocity of midpoint again?
हाँ. I'll just let people copy this. एक बार हो गया बता दो. मिड पॉइंट के लिए मैंने जल्दी से बता दिया था कि maybe I'll just show you the derivation. Can I go to the next page? Just to show you like why velocity of midpoint is like that. Just a quick derivation. तो तुम्हें है ना vectors तुमने देखा है ना, vectors में let's say this is point A, okay? So we know कि let's say that's point A, let's say that's point B, right? So ये हो गया A का position vector origin के respect में RA, ठीक है? और ये हो गया B का position vector origin के respect में RB. फिर you guys know your parallelogram law, which tells कि this guy over here is RA plus RB. Okay. Now draw the other diagonal. Okay. And you know कि in a parallelogram diagonals bisect each other. So this meeting point definitely is our midpoint, right? So अब ये vector becomes position vector of the midpoint, right? And as you can see over here, since these bisect, ये जो length है वो पूरा length का आधा है. पूरा length RA plus RB है, तो midpoint तक जो length है वो उसका आधा हो गया. So now think what I have proved. I have proved कि midpoint का position vector is the average of the position vectors of the ends, which is why you get x coordinate of midpoint is x1 plus x2 by 2. Y coordinate midpoint is y1 plus y2 by 2, right? इसको differentiate करो with time. So differentiate with respect to time. Velocity हो जाएगा दोनों side. और एक और बार करो तो acceleration हो जाएगा. So that relation which is true for position is also true for velocity and also true for acceleration. वो हमने वहाँ पे लगाया. तो वहां पे आगे की तरफ 4 था, पीछे की तरफ -2 था. तो सेंटर ये वेक्टर इक्वेशंस है, तो एक डायरेक्शन को पॉजिटिव रखा. तो ऑन दैट नोट your velocity of the center of mass in that case became आगे की तरफ 4, फिर पीछे की तरफ 2, मतलब आगे की तरफ -2 upon 2. So 1 आगे की तरफ. समझा क्या?
Yes, sir.
Good. So we'll maybe take a break over here.
Could you go back to the previous stage?
हाँ. हाँ. Wow, it's been over 2 hours, right? Let's take a 10-minute break and then we'll continue. इसके आगे हम एंगुलर मोमेंटम में जाते हैं. वो सर ने नहीं पढ़ाया ना अब तक.
Yes.
So it's 7:40.
So I have a
हाँ.
guess is angular momentum I into omega. Like
In a very
what I have learned till now that means into it.
it's not the full story. Special case में I omega. ठीक है वो we'll see that, we'll understand that. ठीक है, take a break till अभी 7:40 कुछ हो गया. Let's take a break till 7:50. You know, I don't know very. I think 4th floor में है अच्छा वाला. ये फर्स्ट लेक्चर है क्या ऐसा यहाँ पे?
So we had one on I think Monday.
अच्छा. Same room, same style.
Yeah.
Do you guys prefer coming या online? Which schools are you in? Like मतलब at least कौन से बोर्ड में हो?
CBS.
सभी CBS. अटेंडेंस है कंपलसरी वहाँ पे? हाँ, पेस का ही. अच्छा. Okay. How does that work? तो कोई और इंस्टीट्यूट का इंटीग्रेटेड में है क्या?
It's a government college.
Okay.
So for practical people.
Okay. That's best. You guys have to attend क्या?
Yeah.
How many hours?
4 to 5 hours. 4. Not every day. It's like
अच्छा.
2 days a week.
हाँ. तो उनका जैसा हो गया फिर प्रैक्टिकल्स के लिए वैसा है क्या?
Lectures होते हैं.
अच्छा.
Usually it's online,
अच्छा.
but otherwise we have to go offline.
But online you still have to attend.
Yeah. Attendance is not.
So every day ऐसा 4 hours goes.
If it's online, but yeah, we can do our own work and like.
अच्छा.
So we have to go at 8:40
Oh, okay. Today.
because 8:55 we have last break.
अच्छा. Where are you guys from?
I'm from Palka. I'm from Brussels.
Okay. Where is this?
It is after Vera. No, it's somewhere closer to North.
But I know वसई तो काफी दूर है ना? तो वही एरिया में है क्या? उसके आगे है? उधर कोई सेंटर नहीं है क्या उसके पास?
पर वो फैकल्टीज अच्छी नहीं है.
अच्छा. तो how many hours of travel this is for you?
1 hour 15 minutes.
Yeah. I mean, please leave. You can At least this is good. You can check the recording. बाद में. What about you guys? तुम कहाँ से आते हो?
I'm from Balaram.
You?
Goregaon.
Goregaon. Okay. You picked up quickly, yeah. So your knowledge is from where? Just what your college has taught you? या कुछ से पढ़ रहा था तू?
पता नहीं ऐसे शायद से पहले से आता होगा. I'm not sure. I don't know where I picked it up, but sometimes I read through stuff like that.
Nice. Hey, this is better.
You'll be taking all the lectures for this topic.
Yeah, rotation. Yeah.
What's the next topic after this?
I think most likely gravitation.
Will you be teaching that?
Yeah. So you'll have two tracks. So another teacher will be teaching you heat and thermal.
That is ongoing.
That is, yeah, that's ongoing. Actually, कहाँ तक हुआ है तुम लोग का heat and thermal?
Like we started with heat capacity. Thermal heat capacity.
अच्छा. तो
Thermodynamics is over. So heat capacity.
and KTG is over.
Yeah, KTG is over.
Thermal expansion बाकी है. Heat transfer बाकी है.
Yes.
और MT कब है ये? 27th को.
I think 29. Near that.
Quite a lot is left है. ये तो हो जाएगा. Cool. Let's start then. Ambience. Nobody needs to freshen up or anything. Yeah. Cool. So now heading लिख लो. Angular momentum. This is the next section. Like we've seen kinetic energy, work energy theorem. Sir has been working with that. Okay. By the way, moving on, because Sir did spend some time, I think lecture 8 and 9 were about your work energy theorem. So do try to have a look at that. Okay. We'll share all those links with you. Just try to cover up quickly. And we'll now move on to angular momentum. So angular momentum के लिए भी तो इसका definition lies in its formula as such. We'll start with what is the angular momentum of a particle. We'll start small. Angular momentum of a particle. And moreover, look at how I'm going to write this. Angular momentum of a particle about an axis. About an axis. So that in a way tells you कि यार ये जो angular momentum वाला चीज है, there's not a standalone thing. You can't just say, hey, find angular momentum. It's always defined about an axis, very much like torque. Can't just say find torque. So torque is defined about a specific axis. So ऐसे angular momentum of a particle about an axis हम देखेंगे. That symbol over there, by the way, is L. ठीक है, capital L. And वो उसके ऊपर bar, this means this is a vector quantity, as you will see soon. So अगर मेरे पास मान लो यहाँ पे एक axis है, ठीक है, जिसके about angular momentum चाहिए, okay? And let's say यहाँ पे एक particle है, particle जिसका linear momentum है p, right? So linear momentum, as you guys know, is nothing but mass times velocity. So linear momentum है p. वो particle का position vector, let's say, is r. So that r is the position vector of the particle with respect to the axis जिसके about angular momentum निकालना है, ठीक है? Given all of this, angular momentum is defined as r bar cross p bar. Okay, so there's a cross product involved. Does this kind of formula look familiar to you guys?
That's like the top formula.
It's like the torque formula. तो मैं इधर this brackets में लिखता हूँ. Again, for the new guys, just you will go through this soon. But this is similar to a formula. Is similar to torque is equal to r cross f. Torque is equal to position vector cross force formula. Okay. This this is just the symbol I normally use for torque. This is actually, if you're wondering what this is the Greek alphabet gamma. Okay, and this is capital gamma. This is just gamma. I think the one I saw in your notes was this one. Forget the bar. It was basically this, right? In ulta. नहीं, ulta. ऐसा कुछ था ना? Okay, and that's another very common symbol for torque, and that's basically tau. Another Greek alphabet. This is like the English T. Okay, so tau, gamma, they are symbols. You can use whatever you want. Symbol में कुछ नहीं है. I have a habit of writing this, so I'll just use that. Okay, so gamma, your torque is equal to r cross f. Very similar to that. Now, अभी यहाँ पे the fact that it's similar to that is a good thing, because तुम्हें actually हर बार angular momentum निकालने के लिए कभी अभी तुम्हें cross product लगाना नहीं पड़ेगा practically. Theoretically, that's the formula, that's the way it is. But there's a nice shortcut you might have realized while finding torque. You don't have to always, perform a cross product between the force and the position vector.
We differentiate that angular momentum formula, then we get.
हाँ, वो सही है. हाँ, that's perfect. वो तो आगे जा रहा है, but that's correct. That shows कि angular momentum relates to torque in the way you're saying. But चलो, we'll not jump ahead. But ये जो formula है r cross p, ये जो cross product है, इसको तुम्हें हर बार लेना नहीं पड़ेगा. गुड न्यूज इज कि अच्छा, इसका अगर तुम मैग्नीट्यूड निकालोगे, तुम्हें पता है कि यार अच्छा क्रॉस प्रोडक्ट का मैग्नीट्यूड होता है वेक्टर. हाँ, तो फर्स्ट वेक्टर, सेकंड वेक्टर, साइन ऑफ द एंगल बिटवीन देम. ठीक है, तो आर पी साइन थीटा. अच्छा, व्हाट इज साइन ऑफ द एंगल बिटवीन देम? तो वो समझने के लिए इट्स, बाय द वे, इट्स नॉट दिस एंगल. ठीक है, द एंगल बिटवीन वेक्टर्स, हाँ, इज व्हेन दे आर जॉइंड टेल टू टेल. ठीक है, ये तो अब हेड टू टेल कुछ एंगल हो गया. तो हम क्या करेंगे, हम आर बार को आगे स्लाइड करेंगे, इसको आगे स्लाइड करेंगे तो ऐसा दिखेगा, this is the angle between them, so this is theta. Okay, so sine of that angle is the formula. अब तुम देख सकते हो कि अच्छा यही सेम एंगल यहाँ पे भी दिख रहा है, ये थीटा है, एंड नाउ if I were to club r sin theta together, then r sin theta would become this, r perpendicular. So this is r sin theta. So it's like, it's basically the perpendicular distance from the axis to the momentum वाला line. तो तुम्हें बस क्या करना है, जहां पे भी मोमेंटम है उसको आगे पीछे एक्सटेंड करो, जैसे टॉर्क में भी करते हैं, ठीक है. सो इफ यू डोंट नो दिस, फोर्स के कारण टॉर्क कैसे निकालते हैं, वो फोर्स को आगे पीछे एक्सटेंड करेंगे, ठीक है. फोर्स अगर वैसा है उसको आगे पीछे एक्सटेंड करके एक लाइन बनाएंगे, एंड वो लाइन का डिस्टेंस एक्सिस से निकालेंगे, जिस एक्सिस के अबाउट टॉर्क चाहिए या एल चाहिए, ठीक है. तो वो डिस्टेंस निकालेंगे. दिस डिस्टेंस इज ऑल्सो रिफर्ड टू एज द लीवर आर्म. You may hear me say that's the lever arm, perpendicular distance between this line, जिसके लॉन्ग मोमेंटम या फोर्स है, टेक्निकली वो फोर्स के लिए होता है, बट इस केस में भी बोल सकते हैं perpendicular distance between this line up and the axis. ये अपना lever arm है. So you can see how L, which is rp sin theta, I mean basically L का magnitude, which is r sin theta into p, becomes r perpendicular into p. मतलब it basically becomes your lever arm and perpendicular distance. We'll see some examples वो और समझ में आ जाएगा. तो lever arm into linear momentum. So it's very easy to find the angular momentum due to a point, due to a particle about an axis. What about the direction? हाँ, so you can use the right hand thumb rule. So what does that actually say? So basically अब technically cross product कर लो. You can see in this example r cross p is coming out to be inwards. R cross p is coming out to be inwards. So a nice neat trick. Have you guys, I'm sure you have learned omega के केस में कि जब एक body clockwise घूमता है तब omega inverse होता है. Angular velocity नहीं, अच्छा angular velocity पता है ना. तो angular velocity is actually a vector quantity, ठीक है. तो जो उसका magnitude है, you have understood that v by r वगैरह, but उसका direction, it's assigned a direction either inward or outward, ठीक है. Just assigned a direction like that by convention. So the direction that we assign to it is, अगर body clockwise घूम रहा है using a right hand, clockwise घूम रहा है, the direction assigned is inward, ठीक है. And अगर body anti clockwise घूम रहा है, the direction assigned to it is outward, ठीक है. No motion takes place in that direction, ठीक है. It's just a representation so that we can develop the maths vectorially आगे. Just a representation, ठीक है. तो clockwise घूम रहा है तो inward. तो इसमें भी if you can see r cross p inward आ रहा है, but हम हर बार क्रॉस प्रोडक्ट नहीं लेंगे. हम बस देखेंगे कि ये जब ये पार्टिकल एक्सिस के अबाउट ऐसा मूव कर रहा है, is it similar to moving in an anti-clockwise direction about the axis or a clockwise direction? ऐसा जा रहा है ना. तो सर्कल कंप्लीट करने के लिए तुम्हें क्लॉकवाइज घूमना पड़ेगा, राइट. सो क्लॉकवाइज घूम रहा है इफेक्टिवली, therefore L is in the clockwise sense or it is inward. That's how you get the direction. This takes care of the magnitude of L, but the direction of L will be the same convention that you apply for omega. Same convention is applied for alpha. Same convention is going to be applied over here. The direction of L is, if it's in the clockwise sense, okay, clockwise sense implies inward direction. Okay. Inward direction is represented as an X, right? So as a vector, if an arrow is going away from you, you see the tail of the arrow. So inward direction is represented like that, and anti-clockwise sense the outward direction. So it's very simple so far. Outward direction represented as a dot, like if an arrow is coming towards you. Cool. So that's L. Sometimes what you could also do is you could also write L as you could also treat L as, you could treat it as R P sine theta. I mean, it's one and the same, just to tell you कि P sine theta then would be so it's the perpendicular component of your linear momentum. Ye P cos theta ho gaya. Remember, this momentum only makes the particle move further away. Oh wow. Okay, that momentum only makes the particle move further away. It's this momentum which actually causes or contributes to rotation above the axis. And that is what angular momentum is really concerned with. This guy. Okay, this guy is our important one. So this P perpendicular, yeah, P sine theta. Cat, acha kaun sa? P perpendicular to what? Perpendicular to the line or perpendicular to the radius of that particle. This axis ke about momentum can also be found like that. Ya to R into perpendicular momentum, ya momentum into perpendicular R. Okay, example dekhenge. I mean, I hope you got the idea. प्रोजेक्टाइल मोशन हुआ है, पढ़ा है, रिजल्ट्स याद है, हाइट रेंज का, ठीक, हाँ, I'll write it down. So basically, let's say you have a particle which is projected with velocity u at an angle theta with the horizontal, and this is our point of projection. So what I want you to do is find the angular momentum of the particle. They'll always say about an axis. About, so I'm saying about the point of projection. About the point of projection. जहाँ से फेंका है, उसके about angular momentum निकाल दो. ठीक है? About the point of projection.
At what time?
हाँ. When it is at, or when it is 1 at the highest point, one when it is at the highest point of its motion, and 2 when it is just about to hit the ground. Okay. कर लो. And जिनको नहीं पता projectile motion, just for them, the new guys, this formula दे रहा हूँ. You see what is needed. ये horizontal distance till it hits the ground again is called as range. जिसका formula होता है u square sin 2 theta by g, और ये वाला h max जो है max height जहाँ तक वो राइज करता है, that is u square sin square theta by 2g. ये 2 theta है, वो sin square theta है. See, they just may be important terms in this question. शिव सही है, पहला वाला सही है। शिव सेकंड वाला गलत है, पहला वाला सही है।
Also, can you check the chat?
सॉरी, हाँ वापस भेजा क्या? हाँ अब सही है, नाइस। देखो सो let's understand what the question is saying. Find L of the particle about the point of projection when it is at the highest point. तो एक है कि यार जब वो वहां पे है, you want your angular momentum. तो ये particle यहाँ पे है, particle वहां पे है, axis ये है, this is our axis about the point of projection जहां से फेंका है. And that's what the question means. Now, of course, you can only find this when you know what the momentum is. So at the topmost point, what is the velocity of the particle? क्या होता है?
U cos theta.
U cos theta होता है. क्यों होता है? क्योंकि ये velocity इसका एक horizontal component होगा U cos theta, right? और एक vertical component होगा U sin theta. And this vertical one keeps decreasing and changing as this, as this moves. वो gravity के कारण vertical velocity effect होता है. But there is no horizontal force. ठीक है ना, सिंपल प्रोजेक्टाइल मोशन, हॉरिजॉन्टल फोर्स नहीं है, तो ये हॉरिजॉन्टल वेलोसिटी जितने से आगे फेंका है वो कभी चेंज नहीं होगा, हमेशा u cos थीटा रहेगा. वर्टिकल वाला एट द हाईएस्ट पॉइंट गायब होगा बिकॉज इज नो लॉन्गर राइजिंग, इसके आगे इज गोना स्टार्ट फॉलिंग. तो यहाँ पे वर्टिकल वेलोसिटी गायब हो जाता है एंड यू ओनली हैव दिस हॉरिजॉन्टल वेलोसिटी लेफ्ट. अगेन दैट्स अ वेरी इंपॉर्टेंट कांसेप्ट की टॉप मोस्ट पॉइंट पे एक हॉरिजॉन्टल u cos थीटा वेलोसिटी रह जाता है. With that, you should be able to find what is the angular momentum about the point of projection. So, क्या करेंगे? R perpendicular. So first we, so as we extend, इसको आगे पीछे extend कर लो, और फिर देखो उसका axis से distance कितना है, और दिखता है कि अच्छा axis से distance इतना है. So R perpendicular in this case, the lever arm in this case becomes the height, the max height of the projectile. इसके कारण फर्स्ट वाले का आंसर हो गया L is okay, L is momentum into lever arm, R perpendicular into lever arm, तो height into u cos theta, mu cos theta, momentum mu cos theta. And of course height फिर तुम substitute कर सकते हो. So when you substitute height from that formula, u cube into m sine square theta cos theta. So only this, I mean this last part actually uses projectile motion. नहीं तो काफी अभी जो किया उस पे ही है. Of course वो u cos theta top most point पे velocity होता है, वो जानना है. Second case, when it's about to hit the ground. See, if anyone's not understanding, just let me know. When it's about to hit the ground, velocity क्या होगा?
It would be theta, but minus theta.
हाँ.
Like the angle with the perfect.
And the speed would be the
same.
Symmetric. In fact, this motion is very symmetrical. So simple ground to ground projectile में that angle will again be theta. यहाँ पे theta, वहाँ पे भी theta होगा. ठीक है? Simple सा अच्छा सा curve होता है इसका. And Work energy theorem say we know it's back at the same height, so it should have the same speed just before hitting the ground, right? So that should be the speed u. Now again, यहाँ पे या तो तुम u को आगे पीछे extend कर लो और ये perpendicular distance निकालो, जो हो जाएगा अगर वो थीटा है वहां पे r sin थीटा, तो या तो mu r sin थीटा वैसे लिख सकते हो, या you could also maybe हाँ r per sorry r perpendicular would not be the range. Why? Because see this time your momentum,
Like we have to find out, like I was saying, like अच्छा
ये लाइन, ये जो रेंज जो है ना वो परपेंडिकुलर नहीं है फिलहाल, राइट? तो तुम्हें रेंज का कंपोनेंट लेना पड़ेगा, तो या तो इसको एक्सटेंड करके रेंज का कंपोनेंट ले लो जो r sin थीटा आएगा, या दूसरा ऑप्शन क्या है, मे बी वी कैन ट्राई द अदर वन, द अदर ऑप्शन इज मोमेंटम का कंपोनेंट ले सकते हो. लेट मी जस्ट सी इफ दिस वर्क्स. इसको ओह नाइस, ओके. तो मोमेंटम का कंपोनेंट ले सकते हो. तो मोमेंटम का ये वाला जो कंपोनेंट है वो घुमा ही नहीं रहा है. घुमाने वाला कंपोनेंट कौन सा है? ये वाला, which would be mu sin theta. ठीक है, perpendicular. This is p perpendicular, mu sin theta. Okay, so mu sin theta into this distance, which is the range, that is the angular momentum. You could either of the two, या तो range into sin theta into momentum, या range into momentum sin theta. See, that's the answer. R डाल दोगे. Got it? Did it even? I hope even the new guys, even though this is unfamiliar territory, at least समझ में आ गया? See? So kabhi, I mean, if you're lucky, you may find direct questions on just angular momentum due to a particle. Okay. All right. All right. So with this, we'll move into angular momentum of an extended body. Okay. Of a rigid body. Okay. अब इसका एक्चुअली जो फॉर्मूला है दैट हैज अ थोड़ा वैसा, इफ यू सी द फॉर्मूला विल बी स्लाइटली लॉन्ग डेरिवेशन, थोड़ा मैथमेटिकल हो जाएगा. एंड इफ यू वांट टू सी द derivation maybe sometime outside class I can show you the derivation, but let's just not spend a lot of time in that derivation, and I'll try to show you the same thing result by a simpler route. So what we'll see, before finding the angular momentum of a rigid body about any axis, let's just try to find the angular momentum of a rigid body about the IAOR. Okay, so let's start with that. Okay, so angular momentum of a rigid body about the IAOR. ठीक है, so some fixed axis जिसके about body घूम रहा है, उसके about angular momentum क्या होगा. So let's say ये अपना axis है, let's say ये अपना IAOR है. Let's say like before, यहाँ पे एक particle है मास mi है, दूरी ri है, वेलोसिटी ri ओमेगा है if the body is rotating with an angular velocity of omega. ठीक है, तो वेलोसिटी वैसा, स्पीड वैसा आ रहा है, ओमेगा दिखेगा. And
It would be summation mi ri square omega.
हाँ ठीक है, सो वेरी नाइस. तो एंगुलर मोमेंटम अब पूरा बॉडी का is the vector summation. ठीक है, these are vector quantities. So is the vector summation of हर इंडिविजुअल पार्टिकल का एंगुलर मोमेंटम. ठीक है, अब हर इंडिविजुअल पार्टिकल का एंगुलर मोमेंटम अगर लिखूंगा ना तो देखो क्या आ जाएगा. सो वी नो द फॉर्मूला इज ri into momentum, right? And momentum is mi ri, right? Omega. Now अभी फिलहाल तो मैंने ऐसे ही बार डाल दिया. I know this is the magnitude and I know that it has some direction. But if you think about the direction, क्या आएगा इस एग्जाम्पल में, क्या आएगा?
It would be along omega.
वेरी नाइस. अरे परफेक्ट यार. तो इस एग्जाम्पल में अगर देखोगे ना, इसका जो एंगुलर मोमेंटम का डायरेक्शन आ रहा है वो ओमेगा के ही डायरेक्शन के लॉन्ग आ रहा है, राइट? ये बॉडी कैसा घूम रहा है? क्लॉकवाइज, क्योंकि ओमेगा ही क्लॉकवाइज है, तो एल भी क्लॉकवाइज आ रहा है, तो एल एंड ओमेगा का डायरेक्शन सेम है. सो आई वांट टू राइट अ टर्म व्हिच हैज दिस मैग्नीट्यूड बट द डायरेक्शन which is the same as omega. So a good way to do that is just write this term as it is. ठीक है, and just place the bar over omega. Perfect. Magnitude क्या है? mi ri square omega. Distance into mass into velocity. तो magnitude बराबर है, and अगर मैं ओमेगा के ऊपर बार डाल दूंगा तो डायरेक्शन भी बराबर हो गया. So this is L. अब even I think now the new students can answer. इसके साथ जैसे हमने काइनेटिक एनर्जी के साथ किया था, ओमेगा को बाहर ले लो and this guy left, the familiar term. ठीक है, that is our moment of inertia. All right, so angular momentum about the IAOR, let me put that nicely. ठीक है, this angular momentum about the IAOR is moment of inertia about the IOR into omega. So that is what we have just derived. नोटिस द बार. तो यहाँ पे बार ओमेगा पे है और यहाँ पे एल पे. एल का वही डायरेक्शन है जो ओमेगा का डायरेक्शन है. अभी this is angular momentum of a rigid body about the IOR. Angular momentum of a rigid body about the center of mass, अगर देखेंगे,
So I center of mass omega.
yes, ठीक है. तो why does it work that way? So angular momentum of a rigid body about the center of mass again basically means कि you are going to sit in the frame of the center of mass. ठीक है. So in the frame of the center of mass, think about center of mass, center of mass पे बैठो, and in the frame of the center of mass, ठीक है, it behaves as the IAOR. उसके फ्रेम में वो IAOR की तरह दिखेगा, और उसके फ्रेम में तुम्हें जो एंगुलर मोमेंटम दिखता है वो हम लिख रहे हैं. सेंटर ऑफ मास के फ्रेम में जो एंगुलर मोमेंटम दिख रहा है वो लिखते हैं. तो फ्रेम ऑफ द सेंटर मास इट बिहेव्स एज द IOR. उस फ्रेम में बिकॉज वो IOR की तरह बिहेव कर रहा है, उसके अबाउट एंगुलर मोमेंटम हो जाएगा ICM ओमेगा.
So can we say that in the frame of any point,
हाँ
L, the angular momentum above that.
yes, so any, तो इसमें क्या होगा, यहाँ पे भी अगर कोई रैंडम सा पॉइंट घूम रहा है ना, उसके फ्रेम में बैठोगे तो उसके अबाउट एंगुलर मोमेंटम विल बी आई अबाउट दैट पॉइंट ओमेगा, बोल सकते हो. बिकॉज कोई भी ये समझो, when they say moment of inertia about some axis of the body, that means you sit on that axis. When you sit on that axis in that frame appears to be at rest, so that axis becomes the IOR in that frame. So valid. But I've limited myself to these two because you won't really, unless they're asking you, you won't really find L about any other point. These are still useful to us for certain reasons. These are what we'll apply in questions. So therefore I'm just limiting myself to this. But जो तू बोल रहा है सही है, ठीक है? Maybe I'll add that note as well. So L of a rigid body above the center mass, in the frame of the center mass, it behaves as the IOR. And also add that once you're done with this page. So just say that as a similarly, L about any axis of the rotating body is I about that axis times omega, because in that axis frame, it behaves as the IOR. ये actually you won't really need to use unless question ही वो है, पंखा घूम रहा है, पंखे का टिप के अबाउट ऐसा एंगुलर मोमेंटम निकाल दो, और क्वेश्चन ही पूछ रहा है कोई रैंडम सा मूविंग पॉइंट है, कोई रैंडम सा मूविंग पॉइंट है जो ना ही सेंटर ऑफ मास है, ना ही IOR है, ना ही फिक्स्ड है ना, तो ऐसा रैंडम सा पॉइंट के बाद अगर क्वेश्चन फोर्सफुली पूछ रहे हैं, यू कैन डू दैट, आई ओमेगा कर सकते हैं. But as you're going to see in solving questions, this is not something we are really going to use. The other formulas are going to be useful. And with this, now what I want to do is, I want to write ये अपना main formula है, ठीक है? This actually had a long derivation, and this is the one I'm just trying to condense. And sometime if you want to see that derivation, I can show you. So L about, this is the important one, L about a fixed axis, about any fixed axis. Okay, so any, it need not even be an axis जिसके about the body is rotating. Okay, it need not be the IOR, it can just be some random axis. Body उधर घूम रहा है, इधर में एक fixed axis के about L निकाल सकता हूँ, उसका फॉर्मूला हम देखेंगे, and ये फॉर्मूला का काफी यूजफुल एप्लीकेशंस होगा. So L about any fixed axis. So long story short, this is, see, so if you think about this, let me just maybe draw something. तो मान लो यार यहाँ पे एक अपना एक बॉडी है, ठीक है, ये अपना एक्सिस है, ठीक है, और मान लो अपना सेंटर ऑफ मास ऐसा मूव कर रहा है, ठीक है, मान लो सेंटर ऑफ मास ऐसा मूव कर रहा है, मान लो इसका मास m है और मान लो ये घूम भी रहा है, इसका एंगुलर वेलोसिटी साथ साथ ओमेगा भी है, ठीक है। नाउ सिर्फ वो सिर्फ आगे जाने के कारण, ठीक है, सिर्फ सेंटर ऑफ मास की मोशन के कारण, मान लो ये मूव नहीं कर रहा होता, तो सिर्फ सेंटर ऑफ मास की मोशन के कारण क्या एंगुलर मोमेंटम दिखता था इस एक्सिस के अबाउट? इमेजिन इफ इट वाज नॉट रोटेटिंग, r perpendicular to mvcm, ठीक है। सो जस्ट बिकॉज ऑफ रोटेशन, आई एम जस्ट शोइंग अ वे ऑफ रिमेंबरिंग द रिजल्ट, इट्स नॉट इवन इसको डिराइव करके मतलब एग्जैक्टली ये रिजल्ट आता है, दिस इज जस्ट अ वे ऑफ कंडेंसिंग द रिजल्ट। तो एक है कि हमें पता है कि पार्टिकल के कारण r क्रॉस p होता था, ठीक है। तो यहाँ पे सिर्फ अगेन जस्ट बिकॉज ऑफ द ट्रांसलेशनल एस्पेक्ट, ठीक है, इट विल अगेन बी r क्रॉस p, बट p कौन सा? लीनियर मोमेंटम ऑफ दिस बॉडी इज ऑलवेज mvcm, कोई भी बॉडी का लीनियर मोमेंटम इज मास इनटू किसका वेलोसिटी? सेंटर ऑफ मास का वेलोसिटी, ठीक है। और ये जो r होगा ना, ये जो r होगा, r क्रॉस p जब निकालोगे ना, r परपेंडिकुलर किसका निकालोगे यार? ये पार्टिकल का निकालोगे या ये पार्टिकल का निकालोगे? r परपेंडिकुलर किसका निकालोगे? तो यू विल फाइंड r परपेंडिकुलर सेंटर ऑफ मास के लिए। सो दिस सेंटर ऑफ मास का जो पोजीशन वेक्टर है rcm, दैट क्रॉस mvcm, that cross mvcm. I'll with examples make sure you understand this result. तो ये है एक टर्म सेंटर ऑफ मास के ट्रांसलेशन के कारण। You can see how this result is correct if you shrink the body, make the body very small. The particle sits at the center of mass, right? The center of mass itself becomes the particle. You can see how this result gives you the result for a particle का angular momentum above the axis. तो बस r cross mv हो जाएगा इस केस में। ये एक टर्म है। And the other term is, अब सेंटर ऑफ मास के अबाउट रोटेशन के कारण सेंटर ऑफ मास के फ्रेम में क्या एंगुलर मोमेंटम दिखेगा? बिकॉज ऑफ द रोटेशन, सेंटर ऑफ मास के फ्रेम में हमने इधर देखा था, ये दिखेगा ICM ओमेगा, राइट। तो एक है सेंटर ऑफ मास के फ्रेम में घूमने के कारण, सेंटर ऑफ मास के फ्रेम में घूमने के कारण ICM ओमेगा दिख रहा है, ठीक है। सेंटर ऑफ मास के फ्रेम में घूमने के कारण ICM ओमेगा दिख रहा है। एंड देन स्टेप आउट ऑफ दैट फ्रेम, ग्राउंड के फ्रेम में सेंटर ऑफ मास खुद मूव कर रहा है, जिसके कारण एक RCM क्रॉस MVCM आ रहा है, ठीक है।
So basically, like a movement, if you consider the orbit of Earth and Moon to be circular, then it's like about it's about the sun. We can this formula helps us to calculate the angular momentum of the moon. So it's like that. It's the sum of Earth's angular momentum and the moon.
Yeah, perfect. So what he's trying to say is like, जैसे अर्थ अगर सन के, मानो कैसा भी ऑर्बिट है, अर्थ सन के अराउंड घूम रहा है, अर्थ के अबाउट मून घूम रहा है, सो दिस अप्रोच वुड बी सिमिलर टू फर्स्ट सेइंग कि अरे अर्थ के हिसाब से पहले अर्थ के फ्रेम में मून का है ना, वो एक जो रोटेशन हो रहा है वो एक टेक दैट मोशन इनटू अकाउंट, तो मून का एंगुलर मोमेंटम अर्थ के अराउंड, एंड देन दिस अर्थ एज अ होल इज रोटेटिंग अराउंड द सन, जिसके कारण मून आल्सो इज रोटेटिंग अराउंड द सन। तो मून का मोशन इज अ कॉम्बिनेशन ऑफ द टू, एक अर्थ के अराउंड और फिर अर्थ के साथ साथ सन के अराउंड। सो दिस काइंड ऑफ लाइक दैट, दिस पार्ट इज दैट अर्थ के अराउंड, सेंटर ऑफ मास के अराउंड बॉडी घूम रहा है, और फिर सेंटर ऑफ मास के साथ साथ ये ट्रांसलेट कर रहा है, जिसके कारण ये टर्म है। This is the condensed way. Maybe once we finish rotational mechanics, I'll show you the proof. This is actually the starting point. If you want to, with this, you can get all the other results. Yeah, this is like the proper starting point. See. So now, अब ये result थोड़ा समझ लेते हैं. Okay. प्लीज इसको, जैसे मैंने आज स्टार मार्क एक चीज किया था, कौन सा किया था, अपना काइनेटिक एनर्जी का फॉर्मूला स्टार मार्क किया था, वैसे ही आई मीन दिस रिजल्ट लुक्स बैड, ये लुक्स लाइक समथिंग यू डोंट वांट टू मेमोराइज, बट यार ये करना है, बहुत ही पिवटल, बहुत ही इंपॉर्टेंट फॉर्मूला है, एंड प्रोबेबली यू कुड इवन जस्ट remember just even star mark these two. So ये कौन सा, यहाँ पे ये नहीं, ये वाला, हाँ. So just it'll help to remember this as well. कि IOR के about you have that, and LCM center of mass के about you have that. So technically both of these results, ठीक है, can come from this. ठीक है. Now अब देखो इसको थोड़ा समझते हैं. So let's just say कि I have an axis over here, ठीक है, and let's say ये मेरा axis है. Let's say I have whatever, that's axis. Let's say यहाँ पे I have a random body जिसका let's say velocity उस direction में है v, ठीक है. Let's say v is let's say this is a disk. Let's just take example. Let's say this is a disk, ठीक है, उसका velocity उस direction में है, let's say that's v itself, ठीक है. And let's say this has an omega in this direction, okay. Let's say disk का mass is m, let's say disk का radius is r, okay. And let's say कि this distance, okay, so ये जो distance है, मान लो ये distance 3r. Just to give you an idea of how that term works. So the formula is, इसको आप समझते हैं, ICM omega. Let's break that down. ICM omega bar plus RCM cross MVCM. ठीक है? RCM cross MVCM. First term एक बार देख लो, ICM omega bar. It is a very simple term. ICM का एक सीधा formula होगा for whatever object you're using. Omega का value मान लो दिया रहेगा. So just use that. So in this case, like what is it? And let's say I'm just giving you random value for omega. Let's say omega is 2v upon r. ऐसे एक random value देगा. See? So ICM omega is going to be disk का ICM center के about mr square by 2 formula है. And omega is going to be 2v by r. 2v by r. ठीक है? तो ये हो गया अपना पहला टर्म. And it will be a good idea to keep track of the direction. ठीक है? Because these
So
are.
why?
हाँ बोल.
So why is omega 2v by r?
नहीं अरे they are given, just randomly given.
Oh, okay. I thought it was a derivation.
नहीं, I'm just making up stuff. ये पूरा question का part है. Randomly दे दिया ये सब. तो या अब मैं पूछ रहा हूँ L कितना है, या मैं demonstrate कर रहा हूँ L कितना है. तो इसमें देखो जैसे ओमेगा क्या है, ओमेगा एंटी क्लॉकवाइज था. इट बी अ गुड आइडिया ऑफ somehow noting that, because this is a vector addition, okay, and you will see in a bit what you have to watch out for. तो ये first term है. Second term is R cross MV.
It would be in the opposite direction.
हाँ, तो R cross MV अभी ये इससे भी डरना नहीं है. just इतना ध्यान दो कि R पहले तो V कौन सा, सेंटर ऑफ मास का. so the only velocity you need to think about is सेंटर का velocity, and R भी किसका, सेंटर ऑफ मास का. so just make sure कि तुम सेंटर ऑफ मास का वेलोसिटी पे फोकस कर रहे हो, उसको सेंटर ऑफ मास पे ही ड्रॉ कर रहे हो, और फिर वहां से तुम इसको आगे पीछे एक्सटेंड करोगे. ठीक है? तो सेंटर ऑफ मास का वेलोसिटी लॉजिकली सेंटर ऑफ मास पे डाल दिया, आगे पीछे एक्सटेंड किया, ओके, एंड फिर तुमने लीवर आर्म निकाला. तो यहाँ पे आर लीवर आर्म इज 3r. सेंटर ऑफ मास पे VCM को आगे पीछे एक्सटेंड करो, दैट्स योर लीवर आर्म. तो लीवर आर्म इनटू दैट वेलोसिटी 3r into v. So that's my second term. R cross mv just becomes lever arm into momentum. So 3r, I'm just adding them, 3r into mass into velocity. But again, now just mind you that this is a vector term. This is very similar to वो particle वाला R cross p, right? तब याद है हमने कैसे डिस्कस किया था, हाउ डू वी फाइंड द डायरेक्शन ऑफ दैट एंगुलर मोमेंटम. देखो कि पार्टिकल को एक्सिस के अबाउट सर्कल कंप्लीट करने के लिए क्लॉकवाइज घूमना पड़ रहा है या एंटी क्लॉकवाइज. क्लॉकवाइज इज इनवर्ड्स, एंटी क्लॉकवाइज इज आउटवर्ड्स. तो इस केस में ये घूमते वक्त क्या आ रहा है, what does this term effectively give us? Clockwise. ठीक है, तो center of mass का motion is clockwise, but about the center of mass it's spinning in the anti-clockwise sense, right? So if I have to add these two vectors, these are actually opposite directions, you'll have to subtract them. That's it. So when we say this is a vector addition, it's not complex. You don't have to apply triangle law. It's as simple as just adding two things in the same direction or opposite directions. यहाँ पे they are in the opposite direction. इसको subtract करना पड़ेगा. तो this randomly, let's say, है ना, इसको बस मैं उल्टा कर रहा हूँ. ये एंटी क्लॉकवाइज था, तो इसको क्लॉकवाइज करने के लिए मैं इसको नेगेटिव कर दूंगा. ठीक है, क्लॉकवाइज करने दिस सेम थिंग mr²/2 2v/r in the anti-clockwise direction is the same thing with the minus sign in the clockwise direction. And इसमें r कटेगा, 2 कटेगा, तो I'm actually getting mrv. First term is mrv in the minus mrv technically in the clockwise direction. Next term is 3mrv also in the clockwise direction. ठीक, तो ये माइनस ये प्लस एंड बेसिकली सब्ट्रैक्ट कर रहा है. ठीक है, 2mrv. तो बेसिकली इफ द डायरेक्शंस आर ऑपोजिट, तुम सब्ट्रैक्ट करो, जो बड़ा है वो डोमिनेट करेगा. सो दिस इज योर एंगुलर मोमेंट.
So
हाँ,
suppose instead of PR, it would have been R.
हाँ.
So it would cancel out.
हाँ,
right?
so L would be 0.
That would mean like it's not rotating.
No, it would नहीं, don't draw inferences. That would just tell you that angular momentum is 0. Whatever that means. Angular momentum above that axis is 0.
So it's not necessary if the angular momentum is 0, then it's not rotating.
नहीं, हाँ. ठीक है, angular momentum, his question was angular momentum 0 होने का मतलब बॉडी रोटेट नहीं कर रहा है. आई मीन, should angular momentum being 0 imply कि घूम ही नहीं रहा है? The answer is no. It's as simple as saying should linear momentum 0 होने का मतलब imply कि कोई मूव ही नहीं कर रहा है. It's not true, right? अगर इधर से mv ऐसा एक पार्टिकल गया, उधर से सेम मास का पार्टिकल ऐसा आया सेम वेलोसिटी के साथ, their momentums as a whole will cancel out. You look at the system, momentum is 0, but there is still motion taking place. यहाँ पे in that same notion, तो जब ये अगर r होगा, angular momentum is 0, but there are conflicting rotations taking place. हाँ बोल, किसने सर बोला था? ठीक है, चलो तो हम थोड़ा एक दो एग्जांपल कर लेते हैं. ठीक है, so let's make this concrete. So let's say हाँ प्लीज. Bye-bye. Okay, cool. तो एक क्वेश्चन कर लेते हैं, maybe Nalil, and we'll probably end with that. So let's say I have a pure rolling disc. Okay, and let's say कि ये अपना x axis है, ये अपना y axis है. ओके, x y मतलब तुम्हारी तरफ z axis है टेक्निकली. ठीक है, सो x y and z है, प्योर रोलिंग डिस्क है. ठीक है, let's say this point is A, our lowest point. Let's say this point is B. The pure rolling disc का mass is m, radius is r. Okay, so B is over here, C is over here, r comma 0. D is D is at 2r comma 0. Just थोड़ा practice minus r comma 0. Okay, and I'm telling you कि इसका velocity is v. That's it. Okay, velocity of the center is v. So with this information,
Shouldn't it be 0, comma or like 0, comma?
I'm so sorry. Yeah, ठीक है.
Because it's on the
Cool. I'll change that. And यहाँ से I want you to find L about the center of mass. I want you to find L about A and so on and so forth. So L about center of mass. ये vector है तो try to also answer with the correct direction. So L about center of mass, L about A, L about B, L about C, L about D, L about E. Okay. And ऐसा लग रहा है कि बहुत सारे questions हैं, but they're all interlinked. So as you figure out some terms, the first few questions, बाकी सब जल्दी follow होगा. Okay, so find these things. And this B guy is at the origin. Okay? B is here. C is here. Let's just make a D a little interesting. D को नहीं चलो 0, r कर लो. अमीनो आ रहा है क्या? नहीं आ रहा है. एक भी कोई फर्स्ट वाला.
It should be ICM times omega.
हाँ. So now just make sure you're answering in terms of what is given. So I've given V, M, R, right? So just in terms of that. So you know the formula for ICM, right? Or
Yep.
M R square by 2. M R square by 2, right?
What's the formula for ICM?
हाँ, M R square by 2. Remember, LCM first one is just ICM omega. The other ones try to do with the formula that we saw. Omega, I hope nobody stuck there. Omega क्या होगा? V by R. ना हो गया क्या? अच्छा, दिखाइए.
One ICM omega.
हाँ सही. सेकंड भी सही है. थर्ड क्या है? बी. हाँ सही है. फोर्थ वाला. अच्छा, परफेक्ट. हाँ नहीं, फोर्थ वाला सही हो गया. हाँ ठीक है. फिफ्थ वाला सही है. सिक्स्थ वाला ठीक है. आई थिंक या सही. गुड. ठीक है, चलो डिस्कस करें क्या? तो इसमें like the first one, LCM, angular momentum about the center of mass, very simple. Okay, so this is just ICM omega. Okay, so LCM is ICM omega. You can even see this from the main formula. Main formula may be, if you see that second term RCM cross MECM, वो zero हो जाएगा, क्योंकि RCM is center of mass का position with respect to that axis. अब axis ही center of mass है, so that position vector becomes zero. VCM also, relative velocity, also becomes zero. So LCM is ICM omega, and with that we get ICM is MR square by 2, okay, into V by R. Omega is V by R. Okay? Pure rolling, that was what is being used. Okay, so that's it. So ये MR V by 2. अच्छा, इसका sense omega is clockwise, right? हाँ, omega is clockwise. जब ये आगे जाएगा, so this is definitely going to roll in the clockwise direction. So this is clockwise. Okay? So MRV clockwise. Or if you want to write it, now since I've labeled the axis and all, if you want to write it as a vector, clockwise will be अंदर की तरफ, right? So Z is towards you. I've labeled that. So clockwise would be inverse. So it would become minus K cap. Okay? Minus K cap. कुछ भी चलेगा. Okay? The next one, LA. So as you can see, A is now the lowest point, right, on the
So
body. हाँ, बोल.
Shouldn't it be MRV by 2?
हाँ, I'm so sorry. Yes. ठीक है. फिर next is LA. So LA, since again I want to use that IOR thing, you can notice that A is actually the IOR. It is the lowest point. Is the IOR. So let me use that. So LA is L about IOR, which is I about IOR omega. I mean, that's one way of doing it. I about IOR is MR square by 2 plus MR square. है ना, parallel axis theorem आज काफी देखा. So we'll just jump ahead. 3 by 2 MR square omega, which is V by R. Okay, and this omega is again same thing, same story, clockwise. So which makes this result 3 by 2 MRV. I could have done it with the general formula as well, but that's you're going to see कि B में similar equation दिखेगा. So I'll just reserve that for B. But this is 3 by 2 MRV, and this is of course again in the minus K cap direction. Okay, so just to point out, if it's L about center of mass and if it's L about the IOR, very straightforward. Just go ahead and use I omega. Now BCD is where we are asked to find L about some random point outside, but some random fixed point outside this body. Okay, no doubt so far, right? All clear? अच्छा, तो अब देखो बॉडी के बाहर, वाओ, क्या करे? अच्छा, okay, yeah. Ah. Is it becoming smaller? Did it?
I think it did. Only a part of it became smaller, a part.
सर 15 से बियॉन्ड अगर जाना तो नहीं जा सकते क्या पेजेस? अच्छा, ठीक है, चलो let's just quickly make use of the remaining space. So LB is now अब इसके लिए since this is outside the body, let's just use ICM omega plus RCM cross MVCM. Now notice first and foremost this ICM omega, we've already figured this out. Already उधर तैयार है. So the only new thing for us is RCM cross MVCM. RCM cross. So ICM omega क्या था? MVR by 2 clockwise. MVR by 2 clockwise. What about RCM cross MVCM? This is the new term. And this is just the same as वो particle वाला terms, right? So R cross. Did it not go back to the previous thing?
It would be, I think, like the distance was not.
Huh.
I think markings are still there.
Huh, marking was there.
We wrote that.
sorry. Okay, this is B, C, and that's D. Okay, so did I not write 2R? I'm so sorry. D was 2R. So B is R cross MV. हाँ तो क्या बोल रहा है? R omega V MV इधर पीछे extend कर लो. And what will be the perpendicular distance? So just extend this and keep. The perpendicular distance to B is R. And you can see how this is in the clockwise sense, right? Center of mass of motion is in the clockwise sense. So this term becomes R, perpendicular distance, into MV. This is in the clockwise sense. This adds up to 3 MVR by 2. Very interesting to note कि उसका आंसर और इसका आंसर एक ही है. Both are the same answer.
Yes.
Right? So as we're going to later do this pure rolling के वक्त, L about any point on the road, as this is rolling, L about any point on the road, no matter how far, is going to be the same. Because the perpendicular distance does not really depend on which point on the road you take. दूर भी जाओ तो भी उतना ही आता है. LC का answer, just moving on. LC, again, the first term is the same. MRV by 2. What is the second term?
The perpendicular distance would be 0.
Perpendicular distance will be 0 for C. So the second term is 0. Right? LD, this is where it's a little different. Again, this first term is MRV by 2 clockwise. The second term is so again you can see that the perpendicular distance is R. The only difference is ये अब ऐसा घूम रहा है. If you try to complete the motion around D, है ना, you will notice कि अब anti-clockwise sense में. तो naturally when you work with these vectors R into MV, ये anti-clockwise sense में, तो when you work with them, you'll have to subtract. And because this guy is bigger, okay, the net direction will also be in the anti-clockwise sense. तो ये हो जाएगा MRV by 2 anti-clockwise. Right? बड़े वाले के direction में will remain. So this is, in fact, this is MRV by 2 K cap. MRV by 2 K cap. Rest were all minus K cap. I think you got the idea. LE का भी जल्दी से answer. LE, last one. ICM omega. Remember, this is always the easiest term. कुछ दिक्कत नहीं है ICM omega में. R cross MV is also easy. इसमें बस lever arm. Just 2R. That's it. 2R. Lever arm 2R. Momentum. थोड़ा सोच के देखो direction. अच्छा ये भी complete करने के लिए ये भी clockwise है. Clockwise, both are in the same direction. Both add up. Comes 2.5. Minus K cap के along. All right. That's it. We'll wrap it up over there.
Excuse me, sir.
Ha.
Can you explain the direction of MRV in LD?
Ha. So LD देख तो right, so this term, so this is our axis, and imagine कि तुम्हारा ये center mass is basically, imagine this is like a particle which needs to complete a trip around D. So just see ये कैसे घूमेगा to complete a trip around D. If it has to be seen rotating around D, the only way I can further imagine the rest of the circle is such that ये अब anti-clockwise turn करके D के round एक trip complete करेगा, right? When the points were below it, notice कि it had to rotate in the clockwise sense to, let's say, rotate about D or rotate about E. But for it to rotate about D, point ऊपर है, particle नीचे से right की तरफ जा रहा है. You can only imagine completing the circle by drawing an anti-clockwise loop. Got it?
Got it, sir.
All right. Cool. Okay, that's it. I'll give you guys some homework, but maybe you're all there on the group, the doubt group.
No, not the doubt.
Acha. You're also not there, right?
Not the doubt.
You're there. Acha. Sir, आप wrap up कर सकते हो. So I'll give you my number. Just
I think I have.
okay. So just message me. I'll give you a link to that group. I'll give you some homework from. You all have the booklet.
Yeah.
And sir has been giving you homework from the booklet.
He was following the illustration.
Okay.
Yeah.
Okay. So Shiv, you can sign out. I'll give you.
This is you, right?
Yeah. I'll post the homework on the group. Okay, Shiv.
So the physics doubt support
Physics
23
doubts.
group.
Yeah. I'll just post it on that. Okay.
Goodbye, sir.
Bye bye.
Sir?